All right, people. I believe everybody is doing great, nice, and absolutely fine. Let me know in the live chat if I am audible and visible properly. Everyone, if I am audible and visible properly. Just a second. Let me fix up everything. Okay. Everybody, am I audible and visible properly? Great, great, great. So we'll have to finish this entire chapter today, okay? We'll be killing each and every single thing over here. Every single concept we'll be basically talking about from the scratch, and I'll be showing you the tons and tons of problems over here. So welcome to Unacademy NEET English. If you have not subscribed to the channel, hit the subscribe button, and most importantly, like this session as soon as possible, okay? That's mandatory. Marking the attendance is mandatory. Like this session as soon as possible. So we'll have to basically study the EMI today, okay? We'll be doing the complete chapter from the scratch, and I'll take you to the level which you actually need when it comes to the NEET exam, okay? So we'll be starting from the scratch. All problem patterns, every question we'll be dealing over here only. I'll be showing you every pattern of question, okay? Variety of problems will be there, and the theory will be completely from the scratch, and it will be to the point, okay? Great, great, great. Everybody. So how is everything going? Okay. Great, great. So guys, like this session as soon as possible. And before this, let me basically just tell you something about this. That is nothing but unlock the power learning, okay? And save up to 35% on a NEET UG subscription. So basically, if you take the NEET UG 2024, this subscription, it will be only for 10,999. And this is NEET UG 2025. This will be 27. You can basically use my code, that is Yawar, okay? And most importantly, I just need to tell you over here, that is this batch, okay? This batch is basically end game batch 2.0, which we have launched. This is the 2.0. So if you want to basically learn from the scratch from the top educators, okay, I am personally teaching in this batch. Wasim sir is teaching in this batch. HSP sir, Kailash sir. So we are teaching in this particular batch, okay? So there are tests, each and everything, okay, is sorted over there. And you can enroll in this batch, okay? The link is in the description below. If you want to learn from personally from us inside Unacademy, you can exactly do that, okay? Great, great, great. Now guys, let me just tell you about that is nothing but, we say, magnetic flux over here. Magnetic flux over here. This is the first topic that we will be dealing over here. Is everybody ready? Shall I start the lecture? Is everyone ready over here? Let me know in the live chat, everybody of you. Shall we start it? Good evening, good evening, good evening. Okay. Let's talk about the magnetic flux. Listen to me very, very, very carefully. This is the first topic that we will be basically talking about in the today's session. What this magnetic flux is all about. It is exactly like electric flux, which I have told you before. Listen to me very, very, very carefully over here. Let's suppose I have placed a magnet over here. Let's suppose I have placed a magnet over here. This is the magnet which I have placed over here, okay? And we say, sir, if I am placing some sort of magnet over here, from the magnet, magnetic field lines are coming out. So these are the magnetic field lines which are coming out of the magnet. These are the magnetic field lines which are coming out of the magnet. We represent magnetic field with the help of magnetic field lines. If you say, sir, I place a magnet over here, it creates the magnetic field. we represent that magnetic field with the help of magnetic field lines. And when it comes to the electric field, we represent electric field with the help of electric field lines. So we say this is the magnetic field over here. And if I suppose say I place a surface in front of this, I am placing a surface over here. Okay. Sir, what does this surface mean? Let me just tell you over here. Let's suppose I have, this is the magnetic field lines. These are the magnetic field lines. And I place a sheet over here. Okay. This is a surface sheet, whatever you call it. Now these magnetic field lines are crossing this particular surface. Okay. So we say over here, listen to me very carefully. This magnetic field line is crossing this surface. This line is also crossing the surface. This line is also crossing the surface. Cool. Now, if I say over here, I'll place another surface over here. Another surface over here. Let's call this as surface A and this is surface B. And we say over here through this surface, we say another magnetic field lines are crossing. These are the magnetic field lines crossing this surface. Now, can you guys tell me how many number of field lines are crossing this particular surface? You say, sir, 3. So we say over here, sir, flux is nothing but 3. And this flux is what we call the magnetic flux. We represent magnetic flux with phi B. This is phi. And when it comes to the electric flux, we say phi E. Phi E means the electric flux. So we say in this case, magnetic flux is 3. Sir, when it comes to this surface, we say over here, magnetic flux is nothing but we say 4. So in this particular case, we say magnetic flux is 3. And in this particular case, we say magnetic flux is 4. Yes, sir. So can I say from this? I'll write the definition over here. Sir, this magnetic flux, it is nothing but it is the number of magnetic field lines crossing the surface perpendicularly. Okay. So how many number of field lines are crossing the surface perpendicularly? That's we call magnetic flux. That's what we call magnetic flux. Okay. So over here we say flux is 3. Why? Because 3 lines are crossing this particular surface perpendicularly. Perpendicularly means over here, if you are it is falling perpendicularly on this. It is making angle 90. So that's why we say magnetic flux in this case is 3 and magnetic flux in this case is 4. Okay. Now listen to me very carefully, my dear people. Let's suppose I say more number of field lines are crossing, more number of field lines are coming from over here. We say, sir, in that case, more will be the flux. Yes, sir, more field lines are crossing, more is the magnetic flux. Sir, can I say this magnetic flux is proportional to magnetic field? Yes. More is the magnetic field, more will be the magnetic flux. As simple as that. Yes. Now, sir, if I say I'll place a bigger area over here, let me just show you on this one. Let's suppose I'll place a bigger area over here. Let's suppose I'm placing a bigger area over here. Now, through this bigger area, we say, sir, more number of field lines can cross. So we say in this case, flux will be large. If more number of field lines will cross through the surface area, we say, sir, flux in that case is large. So can I say, sir, this magnetic flux is proportional to area also? Yes. This magnetic flux is proportional to the magnetic field. This magnetic flux is proportional to the area. Okay. So we say magnetic flux is proportional to the magnetic field. Magnetic flux is proportional to the area. Now on combining these two, we say magnetic flux is nothing but that is B dot A. Or you can simply say, sir, this magnetic flux is nothing but, sir, BA cos of theta. B dot A is also BA cos of theta. Is that clear, my dear people? Is that clear? Magnetic flux is simply the number of magnetic field lines crossing the surface More the number of magnetic field lines crossing the surface, more is the flux. Less are the magnetic field lines crossing the surface, less is the flux. And how to find the magnetic flux? We say, sir, BA, or we say BA cos of theta, B dot A or BA cos of theta. As simple as that. Is that clear, my dear people? Let me know in the live chat, everybody. I want all of you to let me know in the live chat, everybody of you. Is that clear, guys? Is that clear? Let me know in the live chat. Great. And make sure you like this session. If you have not liked the session, like it as soon as possible. Okay. Now see. Now, let me basically take a question over here. We have this particular question over here. This is the question we have. See, we have this infinitely long wire. This is the infinitely long wire we have actually, okay? This is the infinitely long wire, okay? Okay, before this, I'll give you some other question. Let's suppose I say I have a wire over here, okay? Current I is flowing through the wire, okay? Yes, sir. And I'll place a ring over here or a coil over here. Now, can you tell me, because of this wire, sir, how much will be the magnetic flux through this? Or don't tell me how much, we'll see that later. Tell me, flux through this will be zero or non-zero. Let me just tell you. See, when it comes to this wire in which current is flowing, sir, because of this wire, it will produce the magnetic field over here. Okay, yes. Now, how to find the magnetic field? We know whenever the current flows through a wire, it produces the magnetic field. So because of this wire, it produces the magnetic field over here. How to find the direction of that magnetic field? Place your thumb along the direction of current, then curl your fingers. So we say over here, magnetic field in this case over here is basically inwards. Okay. Because of this wire, magnetic field is inwards. Now we say, sir, this magnetic field is crossing the coil. So whenever the magnetic field lines cross the surface, we say magnetic flux is over there. So in this case, we say, sir, magnetic flux is not equal to zero. It is non-zero. As simple as that. Now, my dear people, if I say over here, can you tell me what is the value of magnetic flux in this case? What is the value of, let's suppose this is a wire we have in which current I is flowing, and we have placed this coil over here. We have placed, this is a wire and we have placed the coil over here. Will the magnetic flux through the coil be zero or non-zero? Will the magnetic flux through the coil be zero or non-zero? See. I'll tell you. Sir, if I place my thumb along the direction of current, so from this side, magnetic field is inwards. I show that, I represent that magnetic field with the help of this cross. Okay. Now, come on to this side. Place your thumb along the direction of current and curl your fingers. Now, because of this, the magnetic field is coming outwards. This is outward, this is outward. So the number of magnetic field lines which are going in is equal to the magnetic field lines coming out. So in this case, we say, sir, net magnetic field is zero through this coil, through this surface. Net magnetic field is zero. Okay. So because the number of field lines going in is equal to the number of field lines going out. Let's talk about the next question over here. Okay, simply you just see, sir, how many number of field lines are crossing the surface, and the number of field lines, if the number of field lines going in is equal to the number of field lines coming out, we say net magnetic field is zero in that case. Okay. Now we have this ring over here. Let's suppose this is a coil. This is a coil, and I have placed a ring something like this. Okay. It is something like this in 3D. Previously, I have placed the ring. If this was a coil, I have placed a ring something like this, Okay. Now the ring is something like this. Try to understand this particular fact. So can you guys tell me how much is the flux in this particular case? Can you guys tell me in the live chat? How much is the flux in this particular case? In this particular case, how much is the magnetic flux? flux through this coil. Find, we say find the flux through the ring. Find the flux through the ring. Yes. See how? Let me just tell you, if you place your thumb along the direction of current, it creates the magnetic field over here. Place your thumb along the direction of current and it creates the magnetic field. So magnetic field will be in circular shape. So it will be something like this. This will be the magnetic field in this case. Okay. How? Place your thumb along the direction of current and this is the direction of magnetic field. It formed the magnetic field, form the circular rings over here. So we say in this case, this is the magnetic field. This is the magnetic field over here. This is the magnetic field. Do you think this magnetic field is crossing the surface? We say, sir, no, but it is touching the surface. See, if I say, sir, does this magnetic field cross the surface? We say yes. Now, if I say, does this magnetic field cross the surface? No, it is just touching the surface. So this one is crossing the surface. This is just touching the surface. So we say over here, we say here, magnetic field, we say here, in this particular case, we say magnetic field is not crossing the ring. In this particular case, we say magnetic field is not crossing the ring. So flux will be zero in that case. So flux will be zero in that case. Is that clear, my dear people? Is that clear? Is that clear? Okay, can you tell me in this particular question, find current I is flowing through the ring. Current I is flowing through the ring. We have this particular ring over here. And in this ring, current I is flowing. You guys are supposed to tell me how much is the magnetic flux through this square loop, which is present at the center of the loop. Which is present at the center of the loop. Can you guys tell me this? See, in this particular case, what the question is, we say, sir, if we have to find the flux, we say, sir, flux is simply that is B into A. Okay, B A cos theta. Cool. Now, sir, what is theta? Theta is the angle between B and A. B A cos theta. Theta is the angle between magnetic field and area. Listen to me very carefully. Sir, we say in this question, listen to me very carefully. We have to find the magnetic flux through this square loop. To find the flux through the square loop. We have to find the flux through this square loop. Okay. Now, if we have to find the flux through the square loop, we have to first see how much is the magnetic field crossing through the square loop. If we get that magnetic field, and we'll multiply with the area of the loop, and we'll get the magnetic flux. As simple as that. Now, I'll just write over here. My dear people, listen to me very carefully. I'll just write, we say magnetic field crossing through the square loop. Let's find the magnetic field crossing through the square loop. Listen to me very carefully. Sir, when it comes to the magnetic field crossing through the square loop, we say, sir, that magnetic field is, listen to me very carefully. We have this ring. In this ring, current I is flowing. We know, sir, whenever the current flows through a conductor or a ring, it produces the magnetic field. So because of this ring, magnetic field at the center is, which I have told you in the previous one shot, that is, we say B is equal to mu naught I divided by 2R. Mu naught I by 2R. If you have a ring over here and through the ring current I is flowing, how much is the magnetic field produced at the center? We say mu naught I divided by 2R. where r is the radius of the ring in that particular case. Now, if this coil, if this ring produces magnetic field at center, and that magnetic field is basically crossing this particular area. So magnetic field is crossing the area, so flux will be produced. So we say, sir, magnetic flux is nothing but B into A. What is the value of magnetic field? We say, sir, mu naught I divided by, we say, sir, 2R. And when it comes to area of this ring, we say area of this ring is nothing but L square. Okay, because this is square, side square. And one more condition over here is make sure L is much less than the length of this square is much less than the radius. Okay, then only this formula is valid. So this will be the magnetic flux at the center. This will be the magnetic flux at the center. Is that clear? Is that clear? Is that clear, my dear people? Let me know in the live chat. Is everything sorted over here? Is that clear? Is that clear, my dear people? Let me know in the live chat. Okay. Okay. Now, let's have a look on the next question. Over here, find the flux through the ring. See, it is just opposite of this one. Over here, we have a ring and we were supposed to find the magnetic flux through the square loop. Now, in this particular question, we have a ring and we are supposed to find the magnetic flux through this coil, through this ring. We have a square loop over here. And current I is flowing through the square loop and we have to find the magnetic flux through the ring. Can you guys solve it before I do it? Can you guys solve it before I do it? See, over here, listen to me very carefully. This square loop will create the magnetic field, okay? We know how to find the magnetic field due to a square loop at the center. Listen to me very carefully. We say here, magnetic field is produced by the square loop at center. Why? Because current is flowing through the square loop. So this square loop produces the magnetic field at center. And I'll just write that crosses through the ring. That crosses through the ring. Now, if the magnetic field is crossing through the ring, we say, sir, magnetic flux will be produced. Whenever the magnetic field lines are crossing through the surface, we say magnetic field is produced, magnetic flux is produced. And that magnetic field will be B is equal. Magnetic field due to a square loop is how much? We say 2√2 mu naught I divided by pi into L, where L is the length of the square loop. Sir, have you shown this before? Yes. In the previous marathon of magnetism, I have shown each and every single question of this magnetism. How to find the magnetic field because of the square loop at the center. This I have shown you in the previous marathon. So directly you can remember, magnetic field due to a square loop at center is how much? 2√2 mu naught I. I is what? Current in the square loop. Pi. L. L is the length of this square loop. Okay, this is the magnetic field. Now, if I have to find the magnetic flux, so we say, sir, magnetic flux is nothing but BA. Okay, B into A cos theta. Cos is over here. How much? We say 0 degrees. Okay. Now, angle between area. Area of this is something like this. Okay. And we say magnetic field is also perpendicular over here. Now see, we say in this particular case, sir, this is magnetic fluxes. Instead of magnetic field, we write 2√2 and then we have mu naught I, then we have divided by pi into L. And when it comes to the area, we have to take the area of a ring because field lines are crossing the area. And area of a ring is, we say, sir, pi r square. Okay, this pi and this will get cancelled out over here. Magnetic flux will be 2√2, we say mu naught I into r square divided by, we say, L. Okay, is that clear? Is that clear, my dear people? Let me know in the live chat, guys. Okay. Great, 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 great. This is the magnetic flux through the square loop, and make sure in this particular case also, L is much, much greater than the radius of the ring. L is much, much greater than the radius of the ring. Next question we have over here. Okay, we have the solenoid. Okay. And in the solenoid, we say, sir, current I is flowing. What does solenoid mean? Solenoid means you have a coil. Okay. This is not, see, if we talk about this particular coil, this coil has only one turn. It is one ring. It is just one ring. And if we talk about the coil of multiple rings, n turns, this is the ring of n turns. Okay. So this is what we call the solenoid. This is a ring, but it is having many turns. This is a circular loop with many turns. That's what we call the solenoid. And listen to me very carefully. Remember, my dear people, when it comes to the solenoid, we say if you are sending the current something like this, we say, sir, because of the current, magnetic field is being produced. Because of the current, magnetic field is being produced. So we say over here, sir, this is the magnetic field which is being produced over here. This is the magnetic field which is being produced. Okay. And this is the magnetic field which is being produced. This is the magnetic field. When it comes to the solenoid, we say magnetic field is produced inside the solenoid. You have a solenoid, okay? And in this solenoid, in this coil, this is a coil. In this coil, if current is flowing, it produces the magnetic field something like this, okay? And you have placed a rectangular loop in this one. This is the rectangular loop that you have over here. Now, you guys are supposed to tell me what is the magnetic field, what is the magnetic flux through this rectangular loop. Now, in this particular case, you tell me, sir, magnetic field due to the solenoid is something like this. A rectangular loop is something like this. Does these magnetic field lines cross the loop or just touch the loop? Does these magnetic field lines touch the loop or cross the loop? Let me know in the live chat. These magnetic field lines are crossing the loop or just touching the loop? Yes, we say just touching the loop. So if these field lines are not crossing the loop, we say no flux is being produced. We say no flux is being produced. Here, field lines are not crossing the loop. So no flux is being produced. So no flux is being produced in that case. So flux in that case is, we say, 0. Magnetic flux in that case is, we say, 0. Is that clear? Is that clear? We say flux through this rectangular loop in this case is 0. Next question we have over here. Yes, this is actually a good question. This is a square loop over here. Square loop. This is a square loop placed over here. And we have a current carrying wire. This is infinitely long wire. In this, I current is flowing. You guys are supposed to tell me how much is the magnetic field through this particular loop. Sir, we have a wire in which I current is flowing. And we have a loop which is placed at a distance. This is a square loop, not a rectangular loop. So we say length of this is L and this length is also L. This is also L. You guys are supposed to tell me in this particular case, how much is the magnetic flux through this square loop? How much is the magnetic flux through this square loop? Can you tell me in the live chat? How much is the magnetic flux through the square loop? Everybody, the ones who have not liked the session, like it as soon as possible because it is mandatory, guys. Can you solve this particular question over here? Can you solve this particular question over here? How much is the magnetic flux through the loop? How much is the magnetic flux through the loop? Through this loop. Listen to me very carefully. Sir, When it comes to the magnetic flux, we say it is nothing but B into A. Okay. Sir, if we have to find the magnetic flux through this loop, if you get the magnetic field and if you get the area, you'll get the magnetic flux. Now see, sir, magnetic field through the square loop. We say, sir, magnetic field through the square loop. See, sir, this is an infinitely long wire. Because of the infinitely long wire, it will produce the magnetic field. Yes, sir. Now see, if you have a wire, place your thumb along the direction of current and it is pointing inwards. We say because of this wire, magnetic field is being produced over here. Okay. Magnetic field is being produced because of this particular wire. Can you tell me how much is that magnetic field? Because of the infinitely long wire, magnetic field will be, see, sir, at this point, we say, sir, magnetic field is B is equal to mu naught I divided by 2 pi and this R. If I say this is a wire, at R distance, because of this infinite wire, how much is the magnetic field? This is the magnetic field. Now, the question in this case is, sir, shall I take this A distance instead of R? Shall I take this distance? Shall I take this distance? Which distance I am supposed to take? See, guys, over here, this magnetic field is variable. This magnetic field is variable. Why? Because at this particular point, the value of R is this much. R is the distance from the wire. And when it comes to this point, R is this much. When it comes to this point, R is this much. So R in this case is changing. If this R is changing, we say, sir, magnetic field is changing. So if R increases, magnetic field is decreasing. So what we can do over here, what we can do in this particular case, we say over here, listen to me very carefully how I'll make you this understand. This is a very good question. We say here, magnetic field through the loop is changing. Your magnetic field through the square loop is changing. Okay. At different points, magnetic field is different. Now see, sir, let's do one thing. Let's take a small strip. Let's take a small strip in this particular case. Let's take a small strip. Okay. This is infinitely small. And the width of this is, let's suppose, a dx. And this is placed at x distance from the wire. Let's call this as x distance. And the length of the width is L, because this is L over here. Yes. Now, can you tell me, sir, because of this wire at this x distance, magnetic field will be constant. Because of this wire at x distance, magnetic field is constant through this small strip. Yes, sir. Now, in this particular case, sir, if we talk about in this one, if we talk about, sir, this, because of this magnetic field at this particular point is, we say B is equal to mu naught I divided by 2 pi into x. Why? Because this point is at x distance from the wire. This is the magnetic field because of this wire at x distance. Now, if we have to find the flux, listen to me very carefully. Listen to me very carefully. This is the magnetic field. Now, if we have to find the flux, we say over here, now, flux through the small strip. See, flux through the entire loop, because of this wire, flux through the entire loop is large. Flux through this small strip will be small. So let's call that as a d phi. And this d phi is equal to B into A. How much is the magnetic field through this one? That is, we say, sir, mu naught I divided by 2 pi x. And we have, this is the magnetic field into area. What is the area of this one? We say area of this one is length into breadth. That is L and dx, L dx. So this is the magnetic flux through the small strip. But we have to find the magnetic flux through the entire loop, through the entire square loop. So what we can do is integrate. So we'll integrate d phi is equal to integration of mu naught I divided by 2 pi x, and then we have L dx. We have L dx. Now, what is, see, integration of d phi is nothing but, we say, sir, phi, because it is phi. Now, what is constant over here? What is constant? Mu naught is constant, I is constant, 2 is constant, pi is constant, L is constant. So we can take this out. That is mu naught I divided by 2 pi, and then you have this L, 2 pi L. X is variable. Why? Because for this point, X is this much. For this length, X is this much. For this length, X is this much. So we say it becomes integration of 1 by X and dx. Now, my dear people, you just tell me over here one thing. We have to find the magnetic flux through the entire square loop. So we say square loop is from, sir, this distance is, sir, A. This distance is A from the wire. And this distance is how much? This distance is, sir, L. So this square loop is from A to A plus L. So we say in this case, put the limits from A to A plus L. So we say if we integrate it, we know, sir, magnetic flux is mu naught I divided by, we say, sir, 2 pi. Then we have L, and then we say, sir, log of. Then we say, sir, integration of 1 by X is log X. We say, sir, log X over here. Okay. Log X over here. And limits will be from A to A plus L. Okay. And finally, you can write the result, that is mu naught I divided by 2 pi into L. We say log of upper limit A plus L divided by this A. This is the final answer. Is that clear, my dear people? Is this crystalline clear? Let me know in the live chat. Is this clear? Is this clear? See, in this particular question, we were supposed to find the magnetic flux through the entire loop. But we cannot find the magnetic flux through the entire loop directly. Why? Because through the loop, magnetic field was changing. So we took a small strip. We found the magnetic flux through the small strip. And then by the help of integration, we got the flux through the entire loop. Guys, I need the signal from each and everyone. Is this crystalline clear? Is this crystalline clear? Everyone in the live chat. Everyone means everyone. All of you guys, all of you. I'm waiting for everyone. Is this clear? Okay. Now let's talk about, we say Lenz law. What does Lenz law actually mean? What does Lenz law actually mean? What does it say? Okay, great. What does Lenz law actually say? Let me show you with the help of a diagram over here. See, a lot of people feel this Lenz law is difficult. I'll make you understand this in one single go. So I want each one of you to basically listen to me very, very, very carefully. Okay. Now see, this is a magnet we have over here. This is a magnet. This is a magnet. Okay. And this is a loop, circular coil, I have a magnet over here and I have a circular coil over here. I have a magnet and I have a circular coil in front of me. Okay. Now, what I want you guys to basically do is, if I have a magnet, if I have a coil, what I'm doing is that I'll take this magnet close to the coil. Sir, just a second, guys. I'll do one thing. I'll fix the lighting and all. Just a second. Is it visible? Is it visible, guys? Okay, great, great. Now see, so we say we have a magnetic field over here. We say we have a magnetic field over here. Cool? Yes. We say we have a magnetic field over here. We say we have a magnetic field over here. Okay. See, sir, we say we have a magnet over here. I'm taking this magnet close to the coil and I'm taking this magnet away from the coil. So when you are taking this coil closed, when you are taking this magnet close to the coil, we say, sir, magnetic field lines will cross the coil. These magnetic field lines will cross the coil. Okay. So basically, when you are taking this magnet close to the coil, so you are changing the magnetic field through the coil. Sir, it is coming close to the coil. More field lines are crossing the coil. If you are taking this magnet away from the coil, less field lines are crossing the coil. So we say, sure, on taking magnet close to the coil, on taking magnet close to the coil, we say, sir, magnetic field through the coil increases. Magnetic field through the coil increases. If you take magnetic field, if you take this magnet close to the coil, magnetic field through the coil increases. So flux through the coil increases. As simple as that. So when we are taking coil, magnet close to the coil, field increases, flux increases. Why? Because flux is the number of field lines crossing the surface perpendicularly. Yes. Now, listen to me very, very, very carefully. Sir, if flux through the coil increases, if flux through the coil, we say changes. Increases, or you say, sir, changes. Okay. Whenever flux through the coil changes, okay, listen to me very carefully. I'll just write over here. Due to the change in magnetic field through the coil, we say current is produced in the coil. So we observed that current is being produced in the coil. So when you are taking this magnet close to the coil, away from the coil, we say, sir, in this coil, current is basically being produced. This is the current over here. I'm showing over here this one. This is the current. Current is being produced in the coil. Now the question over here is, sir, what is the direction of that current? What is the direction of that current? What is the direction of that current? Okay, that is the question we have. What is the direction of current? Will the current flow in clockwise direction or will the current flow in anti-clockwise direction? That's what we are supposed to see over here. Sir, as of now, you said if we have a coil over here, you are taking the magnet close to the coil, away from the coil. Sir, on taking magnet close to the coil, magnetic field through the coil changes. So because of that change in magnetic field, we observe that current is being produced in the coil. Now the question is, what is the direction of that current? So we say that is given by Lenz law. That direction of current is given by Lenz law. Now listen to me very carefully. I say, I'll write the statement over here, my dear people. I say that is nothing but if the direction, if the magnetic field through the coil increases. If the magnetic field through the coil increases, then current will oppose the magnetic field. So I say, let's suppose you have a coil over here. Sir, through the coil, you are increasing the magnetic field. Sir, the direction of the current in this coil will be in such a way so that it opposes this magnetic field. Sir, I know it will confuse you as of now, but for now, wait for some time, okay? I'll show you the questions, you will get to understand each and everything. Just remember these two statements. And the second point I'll just write, if the magnetic field through the coil, if the magnetic field through the coil decreases, then current will support the magnetic field. Then current will support the magnetic field. This will be the direction of current, okay? Without solving the questions, you won't be able to understand these two statements. Sir, if I just talk about the statement, sir, Lenz law says direction of induced current will be in such a way that it opposes the cause which is producing it, okay? Forget about it. Just the two statements which I told you. Remember these two statements. Sir, if we have a coil over here, you have a magnet. If you take this magnet close to the coil, we say magnetic field through the coil increases. Sir, now the question is what magnetic field through the coil increases? Now the point is, sir, we observed that current starts flowing in the coil. What is the direction of that current? The direction of that current will be, if magnetic field through the coil increases, then current will oppose the magnetic field. And if magnetic field through the coil decreases, if you are taking coil magnet away from the coil, we say magnetic field will decrease. Then in that case, current will support the magnetic field. Without solving the questions, you won't be able to understand these 2 points. Just remember this point and this point. This is the Lenz law. Now let's move on to the questions. I will show you over here. Let's suppose you have this magnetic field, okay? This is the magnetic field which is increasing. And this magnetic field is inwards. This magnetic field is inwards, okay? This is inwards, okay? Now, you have placed a coil. You have placed a square loop inside this magnetic field. Sir, whenever magnetic field through a coil is changing, increasing, decreasing, we say current is being produced in the coil. Here we say current is produced in the coil. Here current is produced in the coil. Okay. Now we have to find the direction of that current. See, sir, when it comes to the magnetic field, it is increasing. If we just have a look at the statement, if magnetic field through the coil is increasing, then current will oppose the magnetic field. Current has to be in such a way that it opposes the magnetic field. Now see, we say over here, listen to me very carefully. If I make the direction of current over here in this direction, something like this, something like this, something like this. This current is what we call clockwise. I is clockwise. Clockwise. Listen to me very carefully. Sir, over here, this current is clockwise. I say, if the current in this case is clockwise, sir, this is what we call the induced current. Listen to me very carefully. If the induced current is clockwise, if the induced current is clockwise, you tell me one thing, sir, if you have a coil and in that coil current is flowing, sir, does that coil produce the magnetic field? Yes, we have studied that. Sir, this coil will also produce the magnetic field. If induced current is clockwise, it will produce induced magnetic field. Sir, which magnetic field is this? This is primary magnetic field. We have placed this coil in the primary magnetic field. Because of the primary magnetic field, current is flowing in the coil. And we are saying the direction of current is clockwise for 5 seconds as of now. And sir, because of this current also, another magnetic field is being produced. That is what we call the induced magnetic field. And sir, could you please tell me the direction of this induced magnetic field? Sir, we can find the direction of this induced magnetic field. How? Sir, curl your fingers along the direction of current. See, something like this. Thumb is pointing inwards. Thumb is pointing inwards. This I have told you in the magnetism. Place your fingers, curl your fingers along the direction of current. Thumb is pointing inwards. So we say B induced is inwards. Okay, B induced is inwards. Sorry, this magnetic field is outwards. This I have told you previously. This is outward. Okay. Because dot means outwards, cross means inwards. Sir, over here in this particular case, if I just make the ring over here, this is the ring. Sir, primary magnetic field is outwards. This is B primary. And because of this, we say current is in this direction, clockwise direction. We don't know if this direction of current is correct or not. Let me just show you. Now, we say, sir, because of this current, another magnetic field is being produced. That is what we call the B induced. And this B induced is inwards. Now you tell me one thing, my dear people. If B primary is outwards, B induced is inwards. Is B inducing opposing the primary magnetic field or supporting the primary magnetic field? Guys, is B induced opposing the primary magnetic field or supporting the primary magnetic field? Supporting means if you have B primary in the forward direction and this B induced is also in the forward direction, it means support. Oppose means if this is in this direction and another one is in this direction, this is oppose. Tell me, guys, is B induced opposing the primary magnetic field or supporting? Everyone. Yes, opposing. Sir, B induced is inwards. This is outwards. So here, direction of current is correct. Direction of current is correct. Why, sir? Because if magnetic field, this is primary magnetic field, through the coil is increases, then current will oppose the magnetic field. Current will be in such a way so that it will oppose the primary magnetic field. That's why I told you in this case, sir, current has to be in the clockwise direction. That's why it will create the inward magnetic field, which opposes the primary magnetic field. Guys, is this crystalline clear? 90% of the students feel this is difficult, this Lenz law. We don't know how to use it, how to find the direction. This is the actual. I'll show you tons and tons of questions on this one. Okay, don't worry about that. But tell me, is this clear with the fire emojis in the live chat? Is this clear with the fire emojis? Is this clear to each and everyone? Great. Let's move on to the next question. Okay, first we'll solve this one. Let me just give you this one. Let's suppose we have this magnetic field. This is inward magnetic field. Okay, this is inward magnetic field. And this magnetic field is decreasing. This magnetic field is decreasing. And you have placed a coil in this one. You are supposed to tell me what is the direction of the current in this coil. What is the direction of the current in this coil? Clockwise or anti-clockwise? Direction of the current in the coil. See, I'll tell you. Sir, B primary is decreasing and is inwards. Okay. If I say, sir, over here, I say direction of current is in this direction. Okay, this is the direction of current. Sir, whenever you place the coil or a square loop in a changing magnetic field, current is being produced. Sir, current is, let's suppose, in this direction. Okay. We say I is clockwise. Sir, we say I is clockwise. Okay. Now, sir, over here magnetic field is decreasing. Let's move on to the statement. If magnetic field through the coil decreases, then current will support the magnetic field. So in this particular case, current has to support the magnetic field. Sir, I induced, we say it is clockwise. Now, sir, we say due to I induced, magnetic field induced, B induced is produced. Can you tell me the direction of that induced magnetic field, sir? The direction of that induced magnetic field will be also inwards. Curl your fingers along the direction of current. Thumb is pointing inwards. That is B induced is also inward. Now you tell me one thing. If I make this coil over here, square loop over here, the primary magnetic field in this particular case is inwards. Primary magnetic field is inwards and that is decreasing. And sir, we say you have to support the decreasing magnetic field and you have to oppose the increasing magnetic field. How will you support the this decreasing magnetic field? By applying the magnetic field in the same direction, that is inward only. So we say that is only possible if the direction of current is, we say, clockwise. If you say direction of current is anti-clockwise over here, then magnetic field induced will be outward. That will oppose it. That is violating the rule. Is that clear? Is that clear, guys? Is this clear? In this particular case, we say, sir, I is clockwise. Is this clear to each and everyone? Great. Now, can you tell me the direction of current over here? Find the direction of induced current. We have a wire over here in which I is flowing, and this is the square loop. Find the direction of induced current in the square loop. Let me know the direction of current in the square loop. See, I'll tell you how to find it, guys. Sir, over here, because of this wire, magnetic field is being produced over here. See, how to find the direction? Place your thumb along the direction of current and curl your fingers. If you curl your fingers, it is outward. So because of this, at this particular point, magnetic field is outward. This is primary magnetic field. And this magnetic field is increasing. Sir, why? Because current is increasing. If current is increasing, magnetic field due to this increasing current is also increasing. So we say over here, sir, B primary is increasing. And this is outward. This is outward. Now, listen to me very carefully. This is outward. Listen to me very carefully over here. Listen to me very carefully over here. See, we say B primary is increasing. Okay, primary magnetic field is increasing and that is outward. Now, sir, we have to support the increasing magnetic field or we have to oppose the primary magnetic field. Obviously, over here, we have to oppose the increasing magnetic field. So in this case, we say, sir, if we have to oppose over here, so we say if the current flows in the clockwise direction, then only it will oppose the primary magnetic field. We say I induced is clockwise. Okay. So B induced is inwards. Okay. Because primary magnetic field is outwards. So induced magnetic field has to be inwards, then only it will oppose this increasing magnetic field. Is that clear, my dear people? So current in this case is in the anti-clockwise direction. Sorry, in clockwise direction. In this case also current is clockwise. Yes. Now, Can you tell me the direction of current in the square loop? In this case, the direction of current is downward and the current is decreasing. Current is downward and it is decreasing. Sir, we say over here, because of this wire, magnetic field will be, place your thumb along the direction of current, curl your fingers over here. Sir, we say magnetic field is inwards. We say magnetic field is inwards. Is that clear, guys? We say over here magnetic field is inwards. Okay, we say magnetic field is inwards. And this is the primary magnetic field. This is the primary magnetic field. Primary magnetic field is inward over here. Okay? And you guys tell me one thing. You guys tell me one thing. If we say, sir, B primary is inward and this B primary is decreasing. Sir, we know the current will be in such a way that it will support the decreasing magnetic field and it will oppose the increasing magnetic field. So if you have to support the decreasing magnetic field, you have to basically say current will flow in the clockwise direction over here. Then only magnetic field induced will be inward. So we say I induced is clockwise. In this case also current is clockwise, and we say B induced is inwards. Okay, so we have to basically support the decreasing magnetic field. Current is clockwise. Great, great, great. Can you tell me in this particular question? Can you tell me in this particular question? You have current I is the constant current over here. And this one is basically moving away from the loop, away from the coil, away from the wire. Can you tell me the direction of current in this case? Can you tell me the direction of current over here? Can you tell me the direction of current? Can you tell me the direction of current in this particular square loop? What is the direction of current in the square loop? See. Sir, if this is moving, if this coil is moving away from the loop, sir, because of this is the constant current, magnetic field will be different at different points, okay? If you are moving away from the loop, so we say because of this wire, at this point, close to the wire, magnetic field is large. If you move away from the wire, magnetic field will decrease. So away from the wire, magnetic field is decreasing. And what is the direction of current? What is the direction of magnetic field? Sir, that is inwards. Place your thumb and we say over here magnetic field is inwards. Okay, this is B primary and it is inwards. Inwards and it is decreasing. Sir, how it is decreasing? Because this loop is moving away from the coil, away from the wire. So through this loop, magnetic field is decreasing. Now we have to support the decreasing magnetic field. So current will be in clockwise direction. If current is clockwise, I is clockwise. If current is clockwise, then only we say, sir, B primary is also in inward. So that's why we are supporting this one. We are supporting this one. Is that clear? Is that clear? Next one. Okay, let's call this as X, this is Y and Z. What is the direction of current in X loop, Y loop and Z loop? What is the direction of current in X loop, Y loop and Z loop? Can you tell me? This X loop is moving in the upward direction. This Z loop is moving towards the loop. This Y loop is moving away from the loop. Can you tell me? And make sure you like this particular session, guys. What is the direction of current in X loop? Sir, when it comes to the direction of current in X loop, see. Sir, this is moving in the upward direction. It is something like this. You have the wire. This is the loop. It is moving something like this. So this is infinitely long wire. This is infinitely long wire. So we say over here, in this particular case, sir, magnetic field because of the wire through this loop remains constant. Why? because this loop is not moving away. This loop is not moving towards. So it is at the same distance. When it reaches over here, it is also at the same distance. So we say magnetic field through the loop is constant. Why? Because the current is constant. Because of the wire, how much is the magnetic field? B is equal to mu naught I divided by 2 pi into R. R is this distance. Sir, R remains constant when it is moving parallel to the wire. R is constant. Sir, current is also constant. Mu naught is constant, 2 is constant, pi is constant, so magnetic field is constant. Sir, if magnetic field through a coil is constant, it is same, it is not changing. We say in that case, sir, we say in that case current will be zero, because current is only being produced through the coil when magnetic field changes through the coil. When magnetic field changes. So over here, so through the X loop, we say magnetic field is constant. Through the X loop, magnetic field is constant. So current is zero. No current basically flows through the loop. Now, when it comes to this one, sir, this is moving away from the loop. If this coil is moving, this square loop is moving away from the loop, we say magnetic field is decreasing through the loop. So we say, sir, and what is the direction of primary magnetic field? That is inward. So we say in this case, sir, we say in this case, B primary is inwards, okay, and is decreasing. So we say current has to be clockwise. Current has to be clockwise. So when current flows through this loop in a clockwise direction, then only it will produce a magnetic field which is also inward. So we say, sir, this induced magnetic field will support the primary magnetic field. If this is inward, this is also inward. And then we have this one. Then we have this one. This one. This one is moving towards the loop. This one is moving towards the loop. This one is moving towards the loop. We say over here, if this is moving towards the loop, B primary through the loop is increasing. And that is inward and is increasing. I'll show you on the next slide. It is something like this. You have a wire, okay? And current is flowing. You have this loop over here. This loop is moving towards the wire. And if this loop is moving towards the wire, we say, sir, magnetic field will increase through the loop. Why? It is moving close to the wire. So we say, and what is the direction of magnetic field? Sir, place your thumb along the direction of current, curl your fingers, and it is inward. So we say magnetic field primary is inward, okay? And it is increasing. So we have to oppose the increasing magnetic field. If you oppose the increasing magnetic field, that is only done if you basically say current in the wire is anti-clockwise. I is anti-clockwise. Current in the wire is anti-clockwise. Okay, if the current in the wire is anti-clockwise, it will produce the magnetic field which is in the outward direction. So we say B induced is outward. B induced is outward. So this B induced is opposing the primary magnetic field, because primary magnetic field is inward. Is that clear? Is it clear to each and everyone, guys? Is it crystalline clear? Let me know with the fire emojis in the live chat. Is this crystalline clear? And make sure you like this session, everybody of you. Is this crystalline clear, guys? With the fire emojis. Okay. Now this question. Can you tell me, find the direction of induced current in the loop? You guys are supposed to tell me the direction of induced current in the loop. Okay, what is the direction of induced current in the loop? This is the loop A, this is the loop B. Sir, this current is moving in the something like this, in the upward direction. Oh, no, it is moving in the downward direction. Okay. So when it comes to this current, it is moving in the downward direction. Sir, because of this current, magnetic field through this loop is, place your thumb along the direction of current, curl your fingers, that is inward. Over here, we say, sir, magnetic field is inward, that is B primary. We say through the loop A, through the loop A, when it comes to loop A, we say, sir, B primary is inward. To the loop A, we say B primary is inward. Okay. And sir, this current is increasing. So magnetic field will be also increasing. This magnetic field will be also increasing. And if primary magnetic field is increasing, we say, sir, the current has to be in such a way so that it opposes the increasing magnetic field. Sir, we say in this case, current has to be in anti-clockwise direction. So we say I is anti-clockwise. Anti-clockwise. Sir, then only it will oppose the primary magnetic field. How? By creating the induced magnetic field. Because of this current, this is the current. Because of this current, magnetic field is outward. Induced magnetic field is, primary magnetic field is inward. Sir, induced magnetic field is outward. We say B induced is outward. Okay. See, B primary is inward, B induced is outward. So we say, sir, this induced magnetic field is opposing the primary magnetic field. So we say B induced is outward. Okay. Can you guys tell me in this case? Can you guys tell me in this case? Over here, in this particular case, what is the direction of current in this particular case? Is the direction clockwise or anti-clockwise? To the loop A, it is anti-clockwise. What is the direction of current in the loop B? See, when it comes to the loop B, the magnetic field is outward. Place your thumb along the direction of current, magnetic field is outward. We say, sir, this is the B primary, okay? And this is, sir, outward. And when it comes to this one, it is increasing because current is increasing. So it is increasing. So we have to oppose the increasing magnetic field. So if you have to oppose this outward magnetic field, you can only oppose it by producing the inward magnetic field. And that is only done if you say, sir, current is in the clockwise direction. So this will be B induced. We say, sir, over here, current is clockwise. Clockwise. And due to this current, B induced is inward. So which is opposing the primary magnetic field. Is this clear to each and every one, guys? Is this clear? Is this clear? Let me know in the live chat. You have this next question. You have this next question. You have a loop, okay? This loop is moving in the inward direction. This loop is basically moving in the magnetic field. And this magnetic field is constant. This is a uniform magnetic field. And magnetic field is present in this region only. Magnetic field is present in this region only. So this loop is basically moving inside this magnetic field. And this magnetic field is constant. It is uniform. It is not changing. So as this loop is moving inside the magnetic field, listen to me very carefully. You guys are supposed to tell me what is the direction of induced current when the loop is at A. This is the A point. This is the A point. When the loop is at B point, when the loop is at C position or point, when the loop is at D position. At A, it is outside the magnetic field. At B, it is going inside the magnetic field. At C, it is completely inside the magnetic field. At D, it is coming out of the magnetic field. You guys are supposed to tell me what is the direction of induced current. I'll just tell you over here. In this case, no magnetic field is crossing the loop because no magnetic field is present over here. Magnetic field is present in this case only, over here only, in this region. So we say over here current is zero. Simply, when no field lines crosses the loop, we say in that case current is zero. In that case current is zero. Is that clear, my dear people? Yes, current is zero at A. Now, you guys tell me one thing. What is the value of current when it is at B? See, while it is at B, it is moving inside the loop. It is moving, crossing the loop. So we say, sir, more field lines are now crossing the loop. So we say at B, magnetic field is inward, okay? And it is increasing. It is increasing. So the direction of current will be in such a way that it opposes the increasing magnetic field. So over here, we say, sir, induced magnetic field will be basically outward. B will be outward. B induced will be outward. Why? Because this induced magnetic field has to oppose the primary magnetic field. This is primary magnetic field, which is inwards. So this is only possible when the direction of current is, we say, anti-clockwise. Okay? Anti-clockwise. Okay? If the current over here is, sir, anti-clockwise, then only it produces the magnetic field which is outward. See? Yes, yes, yes. Now, we say over here, sir, this magnetic field is constant. So constant magnetic field lines are crossing this coil. When magnetic field through a coil is constant, we say in that case, no current is being produced. So we say over here, current is zero because magnetic field is constant. Over here, magnetic field is zero through the coil. Over here, magnetic field is constant. Now, let's move on to this one. So over here, when the loop is coming out of the magnetic field, we say in that case, sir, B is inverse. We know, sir, this B is inverse because it is given. And this is decreasing. This is decreasing. And when primary magnetic field is decreasing, you have to support the decreasing magnetic field. How will you support the decreasing magnetic field? By producing the induced magnetic field also in the same direction, also in the inward direction. So that is only possible if the direction of current is clockwise. That is only possible if the direction of current is clockwise. See, if the direction of current over here is clockwise, it produces the inward magnetic field. It produces the inward magnetic field. Okay, this is the current at A, B, and C, and D. Now, very important question over here. This one is very important. From NEET perspective, it is very important. This is very important from the NEET perspective. Ravi, I'll be sharing the notes, okay? Today, most probably. If not today, tomorrow. Is that clear, guys? Let me know in the live chat. And most importantly, if you have not liked the session, like it as soon as possible. This is a very important question. I'll just tell you how to solve this question. You have to tell me the direction of current in the coil, with respect to observer. With respect to observer. You have to tell me the direction of current in the coil with respect to the observer. Guys, I want every one of you to let me know in the live chat, is this crystalline clear? All of you guys, all the people out there. All the people out there. All the people out there. Zakir Sabha, Tsaka Chepai Bishnu Paranium, Sub break Nim Temesatan Parvini. Kamananyari on a comment. See, you have a coil over here, you have a magnet which is basically moving away from the coil. In this particular case, you guys are supposed to tell me what is the direction of current. What is the direction of current in the coil with respect to the observer? Sir, what is observer? Observer means the person with respect you are talking about. This with respect to this observer. See. Listen to me very carefully over here. I'll make you understand. Let's suppose if you have a coil over here. Listen to me very carefully. If you have a coil over here, something like this, and the direction of current is something like this towards the board. This is what we call, with respect to me, this is we say anti-clockwise. With respect to me, this is anti-clockwise. Now do this experiment at your home later on. Now you move on to the another side. Current was flowing towards the board. Now if I am from this side, sir, for me it looks like it is clockwise. It is clockwise with respect to me. So with respect to the observer, the direction of the current you are supposed to say. If I say I'm the observer and I'm looking at this coil from this side, the current is anti-clockwise. Now if I move to the another side, we say the same current for me is clockwise. Yes. Same current is basically over here. Now see, we say, now over here, you guys are supposed to tell me in this particular loop, what is the direction of current with respect to the observer? This is a different type of question. Sir, you have a magnet over here. Okay, this is the magnet. And this magnet is having, this is a bar magnet. It has south pole and it has north pole. You have a magnet. It has south pole and it has north pole. And in this case, this magnet is basically moving away from the coil. This magnet is moving away from the coil. So if the magnet is moving away from the coil, we say here, magnet is moving away from the coil. We say in this particular case, magnet is moving away from the coil. Okay, yes sir. If magnet is moving away from the coil, so we say magnetic field through the coil decreases. So we say magnetic field through the coil decreases. Now we know, sir, when it comes to the magnetic field, if the magnetic field through the coil is decreasing, we know, sir, this coil will basically try to support the decreasing magnetic field. And if the magnetic field is increasing through the coil, it opposes the increasing magnetic field. We studied this. Lenz law says that if the magnetic field through the coil is decreasing, it will support the decreasing magnetic field. And if the magnetic field through the coil is increasing, it will oppose the magnetic field. It will oppose the magnetic field. It will increase the it will oppose the magnetic field. Now see, sir, we say this coil over here. Sir, if this magnet is moving away from the coil, listen to me very carefully, my dear people. We say magnetic field through the coil is decreasing. So this coil will never want to decrease the magnetic field through it. So it will support it. How does it support? It will create a bar magnet. This is an imaginary bar magnet inside this, or it will create an induced magnetic field inside it, which I told you before. This coil will create the induced magnetic field. We show that induced magnetic field with the help of this bar magnet. And sir, this will be in such a way that it will support it. Okay, this coil will never want to decrease the magnetic field through it. So we say its south pole will be from this side. Sorry, we say its north pole will be from this side and its south pole will be from this side. Why? Because north attracts south. Unlike poles attract each other. Unlike poles attract each other. Unlike poles attract each other. Okay, we say unlike poles attract each other. So this north will be at this point and south will be from the another side. Why? Because this coil will never want to decrease the magnetic field through it. That's why it will basically try to attract this magnet towards itself. Okay, let's suppose I have this coil over here and you have a magnet. Okay, this magnet is coming towards the coil. This is the north pole and this is the south pole. This coil will never want to increase the magnetic field through it. Why? Because coil opposes the increasing magnetic field, and coil supports the decreasing magnetic field. Coil supports the decreasing magnetic field. So we say over here, it will create an imaginary bar magnet inside this. So north pole will be from this side, south pole will be from this side. Then only north will repel the north. This magnet has to repel this increasing magnetic field. This magnet has to support or attract this magnetic field. I hope you got it. I hope you got it. Now listen to me very carefully. Magnetic field through the coil decreases. Now listen to me very carefully. Now see, so here coil will attract that magnet. Now see, leave this discussion. Now the point is, what is the direction of the current in this particular case? Listen to me very carefully. See, I'll write a statement over here. I'll write a statement over here. If the observer sees north pole of the magnet inside the coil. If the observer sees north pole of the magnet inside the coil, then current is anti-clockwise. See, over here in this particular case, this observer is clearly seeing the north pole because south pole is from the another side. So this observer is directly seeing the north pole. So we say, with respect to this observer, the direction of the current in this case will be anti-clockwise. Yes, sir. And I'll write the next statement over here. If the observer sees south pole, then current is clockwise. Okay, these are the two statements that you need to exactly remember over here. If the observer is seeing the north pole, then the current is anti-clockwise. If the observer is seeing the south pole, then the current is clockwise. Now come over here. This is the question we have. You have got a coil A, you have got a coil B, and observer is at this particular point. Observer is placed over here. You guys are supposed to tell me, find the direction of the current in the coil A and coil B. In the coil A and coil B, you guys are supposed to tell me the direction of current. Can you tell me in the live chat? First, what you are supposed to do is that make the imaginary bar magnets over here. That's what you guys are supposed to do. Make the imaginary bar magnets over here. See, the direction of this magnet is towards right. This magnet is moving towards the coil B, and this magnet is moving away from the coil B. This coil will never want to decrease the magnetic field through it, or this coil will never want that this magnet should go away from me. So it will create an imaginary bar magnet inside it. Okay, and this will be its north pole and this will be its south pole. Why, sir? Because this magnet has to attract this primary magnet which is going away. Now this magnet is coming close to the coil B, so coil B will basically repel this magnet. Okay, so it will create an imaginary bar magnet over here. And this will be the north pole and this will be the south pole. Why? Because this has to repel this magnet. Now see, sir, with respect to the observer, when it comes to the coil B, when it comes to the coil A, observer can directly see south because north is from another side. If the observer sees south pole, then current is clockwise. So we say in this case, current is clockwise. I is clockwise. Okay. And if the observer sees north pole, see, this observer sees directly the north pole in this case because south pole is from another side, then current is anti-clockwise. This is the direction of current. Okay. Now, if I give you the same question over here, the question is something like this. Listen to me very carefully. You have a ring. Let's suppose you have this ring. Okay? And you have this another ring over here. Okay? Now, in this particular case, you have a magnet. Okay? You have this magnet. And this magnet is basically moving towards the right. Okay? This is moving towards the right. And this is what we call the coil A, and this is what we call the coil B. And observer I have placed over here. This is the observer. Now you guys are supposed to tell me what is the direction of current in coil A and coil B. What is the direction of current in coil A and coil B? Find the direction. Find the direction of current in coil A and coil B. You guys are supposed to tell me the direction of current in coil A and in coil B. Can you tell me the direction of current in coil A and coil B? Every one of you? See, over here, sir, if I just try to make this magnet is coming close to this magnet. Sir, when it comes to this coil, it will oppose this. Let's suppose this is south and this is north. Sorry, I forgot to tell you. This is south, this is north. We say, sir, over here in this case, if this is north over here, this is south. Because this magnet will oppose this magnet. Why? Because it is coming close to the coil. Now, this coil will basically create a bar magnet over here. This coil will basically create the bar magnet over here. And this will be in this case north, and this will be over here south, because this north will try to attract this magnet over here. Now, this observer is able to see north over here. So in this case, current is anti-clockwise. Okay. And when it comes to this one, this observer is directly able to see south. So in this case, current is clockwise. We say current is clockwise. Is that clear, my dear people? Is that clear? Let me know in the live chat if this is clear to each and every one of you. This one, find the direction of induced current in inner coil where current is decreasing in the outer coil. Okay. This is the outer coil, current is decreasing. You guys are supposed to tell me the direction of current in the inner coil. First, let's find the magnetic field. Sir, curl your fingers along the direction of current. Thumb is pointing inwards. So we say over here, this is the primary magnetic field. We say B primary is inwards. If B primary is inwards and this current is decreasing, so this is also decreasing. Okay, this is also decreasing. So this coil will create the magnetic field in the inward direction also. Why? Because it will support the decreasing magnetic field. So now this will be the inward magnetic field. This is inward magnetic field. So in this case, B induced is also inward. Why? Because this coil has to support the decreasing magnetic field and it has to oppose the increasing magnetic field. So that is only possible if the direction of the current is clockwise. So I is clockwise. In the coil 2. Is that clear, guys? I want every one of you to let me know. In the live chat only. with the fire emojis, everybody. Now you guys are supposed to tell me, in this particular case, the wire changes a circular shape when we have to find the direction of the induced current. See, in this case, this wire is basically going to change in the circular shape. It is something like this. So it is basically expanding. It is expanding. So after some time, it will be a proper circle. So you guys are supposed to tell me, in this particular case, direction of current. See, we say when it comes to the flux or when it comes to the field, see, if the wire expands, if the loop, let's call this as loop, if the loop expands, we say more magnetic field crosses. More magnetic field crosses through it. If the loop expands, we say more magnetic field crosses through it. And if the more magnetic field crosses through it, so we say magnetic field through the loop, B primary is increasing. Magnetic field through the loop is increasing. Okay. If magnetic field through the loop is increasing, we say, sir, and is inward. We say, sir, the current in the loop will be basically, we say, anti-clockwise. Okay. Why, sir? Because if the current is anti-clockwise, then only it will create the induced magnetic field that is in the outward direction. Because this induced magnetic field has to be basically outward, because it has to oppose the increasing magnetic field. It has to oppose the increasing magnetic field. That is only possible if the direction of current is anti-clockwise. This one, okay, this is a good question actually. See, over here, let me just tell you, let's not read the question and let me just tell you directly. You have got over here, this is a region given. Okay, this is a region given. Okay. And in this region, we say magnetic field is present. This is the magnetic field which is present. Magnetic field is present in this area. And a rectangular loop is basically trying to move inside this magnetic field. A rectangular loop is basically moving inside the magnetic field. Okay. So while the rectangular loop is moving inside the magnetic field, let me just show you something like this. It is basically moving inside, and when it is inside, and then it comes out, So loop is moving inside and then it comes out in this particular case. And you guys are supposed to plot in this case the flux time graph. The flux time graph. So this will be the flux and this will be, sir, time. While the loop is moving inside this magnetic field, okay, this is the magnetic field. And in this particular case, you guys are supposed to make the flux time graph. The loop is moving inside and then comes out. You guys are supposed to make the flux time graph. Listen to me very carefully. Sir, when the loop is moving inside, we say, sir, more field lines are crossing the loop. So we say more field lines are crossing the loop, we'll say flux will increase. If more field lines cross the loop, we say flux will increase. We say in that particular case, sir, if the flux is increasing, so graph would be something like this. So we say graph would be something like this, okay? While moving inside, graph is something like this. Flux is increasing. As this loop is going in, field lines are more field lines through the loop are increasing, we say flux is increasing. And while it is inside, we say number of field lines crossing through the loop is constant. Okay, it remains constant. Then it remains constant for some time. Okay, then it remains constant for some time. And afterwards, what happens is that, just a second. Afterwards, what happens is that we say once the loop comes out, again, field lines through the loop will decrease. So the flux will exactly decrease. Okay, flux will exactly decrease. And this flux will increase at a constant rate. Then flux remains constant. Okay, and then it will decrease at a constant rate. Why? Because the loop is uniform. The shape of the loop is uniform over here. This will be the graph. Is this clear, guys? Is this clear? While moving inside, flux is increasing. While coming out, flux is decreasing. Okay, when it is completely out, so flux is 0. Okay? Is this clear? Is this clear? While moving in, we say phi increases, then remains constant. Okay, while moving out, flux decreases, then becomes 0. Is this clear, guys? Let me know in the live chat if this is crystal clear each and everyone. Is that clear? With the fire emojis in the live chat if this is crystal and clear to each and everyone. Let me know in the live chat, guys. Okay, great. Okay, this is the question we have over here. This is the question we have exactly over here. We have an electron, or we have a charge over here. Don't say electron, this is a charge. And this charge is basically moving towards the loop. This charge is moving towards the loop, okay? And then it moves away from the loop. And in this case, you guys are supposed to tell me the direction of current in the loop. You guys are supposed to tell me the direction of current in the loop. See, it is something like this. You have got a loop over here. You have got a loop over here. See, you have got a loop over here. Okay. And you have a charge. Let's suppose this positive charge. And it is moving towards the loop. This is moving towards the loop. This charge is actually moving towards the loop. Okay. This charge is moving towards the loop. And when it is moving towards the loop and when it reaches over here, now it is moving away. As initially it is coming close to the loop and then it moves away from the loop. Sir, when charge flows, we say current is being produced. Let's suppose this is the current. So we say in this particular case, this is the direction of current. This is the current. Now, if this charge comes close to the loop, we say this current kind of comes close to the loop. Yes, sir. Now, because of this current, we say magnetic field will be over here. Magnetic field will be over here in the outward direction. Magnetic field will be over here in the outward direction. How? Place your thumb along the direction of current. Magnetic field is outward. We say in that case, magnetic field is outward. Okay. When charge moves towards the loop. Charge moves towards the loop. Okay. In this case, we say, sir, B primary is outward. We say, sir, B primary is outward. Okay. Now, if B primary is outward, sir, through this loop, magnetic field is outward and it is increasing. It is increasing. Why? Because this charge is coming close to the loop. As the charge comes close to the loop, it will create the current that is in the outward direction. It will create the magnetic field that is in the outward direction, and that magnetic field will be increasing. Now, sir, through this loop, magnetic field is increasing. Okay. If through the loop magnetic field is increasing, so this loop will try to basically oppose the increasing magnetic field. That is only possible if you say the direction of the current is, we say, clockwise. We say clockwise. Okay. And if the direction of current is clockwise, it will create the magnetic field which is in the inward direction. So it will create the magnetic field, induced magnetic field, which is in the inward direction. So B induced is inward. So B induced is inward, which opposes the primary magnetic field. Okay. So when the charge is coming close to the loop, sir, current will create the magnetic field over here. Because current is being produced, it will create the magnetic field that is in the outward direction. And this magnetic field is also increasing. Now in the loop current will flow in the clockwise direction, which creates the inward magnetic field, which opposes the primary magnetic field, which is increasing. Is that clear? Is this clear, guys? Is this clear? Now its second part you will do. Okay. When the charge is away from the loop, find the direction of current. I'll just write over here. The next question is, when the charge moves away from the loop, then find the direction, of current in the loop. This is the part that you will do on your own. Okay. This is the part that you will do on your own. Now comes basically the next one. That is what we call the Faraday's law of electromagnetic induction, EMI. Faraday's law of electromagnetic induction. We need to talk about this one now. Now listen to me very carefully. Let's suppose, my dear people, if I just say over here, I have a loop. I have a circular loop or a circular coil over here. Okay. And I have a magnet over here. This is the magnet. Okay. Yes, sir. And this magnet, my dear people, is coming close to the loop. This magnet is coming close to the loop. Okay. This is the magnet. It is coming close to the loop. So let me just write over here. When the magnet comes close to the loop, when the magnet comes close to the loop, we say magnetic field through the loop increases or changes. We say magnetic field through, we represent magnetic field with B. Magnetic field through the loop changes. Okay. And if the magnetic field through the loop changes, listen to me very carefully. We say, so magnetic flux, that is phi B, through the loop changes. Okay. We say magnetic flux through the loop changes. Yes, sir, 110%. And if the magnetic flux through the loop changes, listen to me very carefully. We say, so current is produced. We know, sir, whenever the magnetic field through the coil changes, current is being produced in the coil. Yes, sir. So my dear people, if current is being produced in the coil, we say if current is being produced in the coil, as we know, sir, current only flows when there is a potential difference. As we know, current flows when there is potential difference. You guys know current only flows when there is potential difference, my dear people. Okay, current only flows when there is potential difference. Okay, so what is potential difference? Potential difference, or we say, sir, EMF. We say EMF because we know, sir, V is equal to I into R from Ohm's law, or V is proportional to, sir, I. According to Ohm's law, V is proportional to I. If there is potential difference, there is current. This I have told you. And more is the value of potential difference or EMF, more is the current in that case. Yes, sir, we have studied this before. Okay. So listen to me very carefully. We say on changing the magnetic field. Okay. If this magnetic field changes, we say because of this, we say magnetic flux changes. And if magnetic flux changes, we say, sir, current is being produced, and this current is being only produced, sir, when there is EMF, when there is potential difference. So can I not say because of this, this comes, because of this, this comes, because of this, this comes? So we say, sir, on changing the magnetic field, EMF is being produced, or on changing the magnetic flux, EMF is being produced. So we can say, on changing the magnetic flux, that is phi B, through the coil, on changing the magnetic flux through the coil, we say EMF is being produced. EMF is being produced. On changing the magnetic flux through the coil, we say EMF is being produced. Now, if I have to write this exactly, I'll just write it in something like this. EMF is equal to, we say that is delta phi divided by delta t. And put the negative sign over here. Why do I have to put the negative sign? Because Lenz law says the direction of this induced EMF or induced current will be in such a way it opposes the cause which is producing it. So this is change in flux. Delta phi means change in flux is equal to the EMF. This is what we call the Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction says that the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through that circuit, through that coil. So change in flux, by changing the flux, EMF is being produced. Now let's talk about, my dear people, let's talk about one thing. What is that? Let's talk about, we say average EMF. Average EMF. Sir, what does average EMF mean? See, when it comes to the average EMF, sir, we have studied average velocity, that is delta S by delta T. Sir, we have studied instantaneous velocity, that is ds by dt. Okay. So over here, delta, that is change in flux. If flux change, total change in flux upon total change in time. So we say average EMF will be EMF, and we say average over here, that is minus delta phi divided by delta t. This is the formula exactly. Okay. And when it comes to the instantaneous EMF, sir, instantaneous potential difference, instantly at a particular point, how much is the EMF which is being produced? So we say, sir, that is nothing but this EMF INS is equal to, that is d phi divided by dt. Sir, can you give us a bit more feel about this? Yes, I can give you the bit more feel over here. Listen to me very carefully. See, Listen to me very carefully. I say, sir, let's suppose from 9 a.m. morning to 1 p.m. From 9 a.m. to 1 p.m. flux was changing continuously. So if flux changes, we say EMF is being produced. So from 9 a.m. to 1 p.m., the EMF which is being produced, that is what we call the average EMF. Total EMF being produced from 9 a.m. to exactly 1 p.m. Now, if I say exactly when the time was 10:30, when the time was 10:30, okay, at that particular point of time, how much EMF is being produced? That EMF is what we call the instantaneous EMF. If I say from 9 a.m. to 1 p.m., flux was changing through the coil, flux was changing. We say EMF was being produced. From 9 a.m. to 1 p.m., the EMF which is being produced, that's what we call the average EMF. When it comes to the instantaneous EMF, that is the EMF which is being produced at a particular instant, particular time. I hope this is clear to each and everyone. Now, if I just write over here, see. One more thing I just want to tell you in this particular case. One more thing I just want to tell you. Sir, as due to the EMF. Sir, when there is EMF or potential difference, EMF, potential difference, one and the same thing. When there is EMF or potential difference, we say current is also produced. Or we say current also flows in the coil. Current also flows in the coil. Now, my dear people, if we just talk about the current, let's find the average current. So let me just write over here to find the average current. Let's find the average current. See, when it comes to the average current, my dear people, sir, I'll just write over here I average. We say, sir, that is simply, listen to me very carefully. We know, sir, when it comes to the current, we say V is equal to I into R. And I can write I is equal to V divided by R. And what is this V? V is nothing but potential difference divided by R. I is equal to V by R. V is potential difference. And this we can write this is EMF divided by Sir R. Now, what is the value of average EMF? If we have to find the average current, we'll put the average EMF. That is delta phi divided by delta T. We say I average will be simply, you say, sir, this is delta phi divided by this R and this is delta T. This is the value of average current which is being produced over here. Now, if I talk about the instantaneous current, to find the IINS. So we say, sir, IINS is equal to EMF divided by R. But over here, we took average. And in this case, we took instantaneous. Okay. And what is the value of instantaneous EMF? That is d phi by dt. So I can write this IINS is equal to d phi divided by R. And this is dt. Okay, this would simply be case in that one. Okay. This is the value of average current and this is the value of instantaneous current. Okay, this is the value of average current and this is the value. Now, we say one more point. Sir, if the current is flowing over here or if the current has flown, we say, sir, charge has also flown. If the current has flown, so charge has, if the current is produced, so charge has flown. That means charge has flown because flow of charge is what we call the current. We say, sir, in this coil, if you change the magnetic flux, you say, sir, current is being produced over here. Current is being produced over here. And if current is being produced, that's because of EMF. And if current is flowing in the coil, let's suppose we say, sir, current is flowing in the coil. Sir, if the current is flowing in the coil means charge is flowing. Current is what? Flow of charge. And how much charge is exactly flowing? We say, sir, let me just write over here, I average is equal to delta phi divided by R delta T, this one, okay? And when it comes to the average current, can you tell me what is the value of current? I is equal to Q by T. And instead of this average, we say, sir, delta Q. We say, sir, this delta Q divided by delta T is equal, we say, sir, delta phi. We say, sir, this delta phi divided by R and this delta T. This and this will cancel out over here. What remains? We say, sir, this delta Q is equal to delta phi divided by R. This was once asked in the NEET. How much is the charge flown in this particular case? So this charge flown does not depend upon the time. So this is basically delta Q. This is not delta Q, this is delta phi. This is flux. This is flux. Delta phi by R. Is that clear? Is that clear? Is that clear? Negative sign basically tells you the direction of the induced current, which I have told you already. The direction of induced current will be in such a way that it opposes the cause. Okay? It opposes the cause. What is the cause? Cause is if the primary magnetic field is increasing, you have to oppose it. That's why we put the negative sign. Negative sign basically tells us the direction of this induced EMF or induced current will be in such a way that it opposes the primary magnetic field. This negative sign tells us that it opposes the primary magnetic field. Is that clear? Is that clear, guys? Let me know in the live chat. Every one of you with the fire emojis in the live chat, if this is crystal and clear. This is the Faraday's law of electromagnetic induction. This is the first question you have on your screen. Which option is correct? Which option is correct over here? You have got a conducting ring of radius R. Okay, we have a ring. Let me just make it over here. You have a ring and its radius is exactly, this radius is exactly given as R. Okay, this radius is given as R. Is placed perpendicularly inside a time varying magnetic field. It is placed in a magnetic field. Let's suppose this is the magnetic field. And this magnetic field is given as B is equal to B naught plus, we say alpha T, B naught plus alpha T. This coil is given, this coil is placed inside a time varying magnetic field. This is placed in a time varying magnetic field. And you guys are supposed to tell me the EMF produced in the ring. How much is the EMF being produced in the ring? See, sir, when it comes to the magnetic field is changing. So whenever the magnetic field, this is changing. Whenever the magnetic field is changing through the coil, we say, sir, EMF is being produced. EMF is produced. Okay? Or potential difference is produced. We are supposed to find that EMF. We know, sir, by changing the magnetic field, flux is being produced. See. Sir, we say when it comes to the EMF, EMF is simply minus d phi divided by dt. Simply. Sir, by changing the magnetic flux, EMF is being produced. Now, if we have to find the EMF in this case, we say minus d by dt of, and flux is what? Flux is magnetic field into area. Okay, flux is B into A. Now, if we just write over here, this EMF would be simply minus d by dt of, what is the magnetic field? That is B naught. That is B naught plus, we say alpha T, okay, into area. Area is how much? Area of this loop, that is simply pi r square. So we can write it something like this over here. So this magnetic field is, see, differentiation of B naught. B naught is a constant, so it will be 0. So differentiation of this one, I can write it over here, minus d by dt of differentiation of what? Differentiation of this is 0. Differentiation of this one, alpha t plus alpha t into pi r square. We say alpha t into pi r square over here. Okay. Alpha t into pi r square. Now, sir, we say, sir, this is b is equal to minus alpha is constant, sir, pi is constant, r is constant, r is the radius of the ring, and this what remains, that is dt by dt. Dt by dt is 1. So this is not magnetic field, sorry. This is EMF. This is EMF. So this EMF will be minus alpha pi into r square. Alpha pi into r square. Minus alpha pi into r square. Option B seems to be the correct option. Yes. Is that clear, guys? Let's move on to the next question we have over here. Okay, we have this question over here. We have this question over here. See, in this particular question, magnetic flux through a circuit of resistance 20 ohms, okay, is changed from 20 Weber to, let's suppose we have got this as a circuit. This is a coil, okay, or this is a circuit. You can call this as a circuit or a coil. And its resistance is, let's suppose, 20 ohms, okay. And magnetic flux changes from 20 to 40 Weber. We say, sir, change in flux is 40 minus 20 in this case, because it changes from 20 to 40. We have got a coil. Magnetic flux through the coil changes from 40 to 20. So 20 to 40. So change will be how much? Final minus initial, 40 minus 20, and that is 20. In 5 milliseconds, charge passed through the circuit during this time is, we have to find the charge. See, magnetic flux is changing through the coil. Yes, sir. We know, sir, whenever the magnetic flux changes through the coil, EMF is being produced, means current will flow, means charge will flow. And what is the value of that charge, my dear people? Over here, I just told you. Delta Q is equal to delta phi divided by R. Charge flown is equal to, as, sir, delta Q is equal to delta phi divided by R. Now, delta Q, we say this delta Q is equal to delta phi, that is 20, divided by R is, we say 20, that is 1 coulomb. 1 coulomb is the charge which is over here. That is 20 by 20 is 1 coulomb. Okay. So 1 coulomb charge has flown. So the next question we have over here, radius of a circular loop. Radius of a circular loop placed in a uniform magnetic field is increasing. Okay. Let me just show you over here. We have a magnetic field. We have a magnetic field. We have a magnetic field. This is the magnetic field. Okay. Yes, sir. And inside this magnetic field, we are placing a loop. We are placing a loop inside this magnetic field. Okay. We are placing a loop inside this magnetic field. And the radius of this loop is R. The radius of this loop is, it is R. Okay. And the radius of this loop is changing. Means this loop is expanding. Okay. The radius of this loop is changing. Okay. The radius of the loop is increasing at a rate. Means over here, dr divided by dt is equal to, we say, R naught meter per second. So every second, how much radius is increased? We say R naught. Now it will be R naught, again R naught, R naught. So it keeps on increasing. Radius of the loop over here is increasing. Radius of the loop in this case is increasing. Okay. And at any instant of, then find the EMF induced. Over here, we have to find the EMF. We say to find EMF. See, my dear people, let me just tell you over here. If the radius is increasing, see, we say, sir, this loop is getting bigger. We say more field lines will cross through the loop. If more field lines will cross through the loop, we say flux or field through the loop is changing. Whenever the field through the loop is changing, we say, sir, EMF is being produced. So that's what we are supposed to find. We have to find that EMF. And we know, sir, this EMF is simply minus d phi divided by dt. Okay, this is the value of EMF. So over here, see, when it comes to the flux changes by changing the area or magnetic field. So we say over here, area is changing, magnetic field is constant, B is constant. Okay, B is constant. Now, if we have to find over here, what is the value of this EMF? This EMF is equal to minus, we say d by dt of, and what is flux? That is B into A. What is flux? That is B into A. And we can write this EMF is equal to minus, this EMF is equal to minus d by dt of, d by dt of, what is the magnetic field? Magnetic field is B. Okay. And what is the area? Area of this is, if this is R, that is, we say, sir, pi r square. Now you guys tell me one thing. In this particular case, take this B and pi out. I can write it something like this. EMF is equal to minus B into pi. B is constant, pi is constant. And then we have dr square divided by dt. Okay, now what we'll do in this particular case is multiply with the dr and divide with dr over here. Now interchange is dr and this dt. So we write minus B into pi. And then we have dr square, take it over here, divided by dr and multiplied by, this is dr divided by dt. Okay. Now over here, sir, minus B into pi. See, differentiation of r square with respect to r. That is how much we say, sir, this is 2r. And dr by dt is given. Rate of change of radius with respect to time is r naught meter per second. So we say this is r naught. So answer would be minus B pi 2r and this r naught. B pi 2r and this r naught. B pi 2r naught and this r. Option D is the correct option. Is that clear? Is that clear, my dear people? Let me know in the live chat. Is it crystal clear to every one of you? And make sure you like this particular session, all the people out there. Let me know in the live chat with the fire emojis if this is crystal and clear to every one of you. This is the question we have. Okay, this is the question we have now. Now, in this particular case, see, what is given is that we have got the magnetic field over here. And this magnetic field is actually present in this B region. Okay, this is the width in which magnetic field is present. And you have a rectangular loop with the velocity V. And this length of the loop is A. Length of the loop is A. Okay. Now, this loop is basically entering this magnetic field over here. This loop is entering the magnetic field over here. Just a second. This is the loop we have got over here. This is the length of the loop. This is the length of the loop. That is A. Length of the loop is A. And this width is actually B. This width is actually B. Now listen to me very, very, very carefully. Listen to me very, very, very carefully. See, you guys are supposed to tell me, find the time up to which current is induced in the loop. See, when this is entering this magnetic field, when this loop is entering the magnetic field, let's suppose this is a loop something like this. This is a loop something. It is entering the magnetic field. See, when it is outside, we say current is zero. Why? Because no field line is crossing the loop. Now, when it starts entering the loop, now field line is increasing. Field lines or flux through the loop is increasing. We say current is induced. Now current is induced. Now it becomes zero. Why? Because field lines through it is constant. And sir, when it comes out, again field lines will through the loop is decreasing, and current is flowing. So when field lines through the loop is changing, or flux through the loop is changing, then only current is being produced. And when field lines, when it is completely inside, we say flux through the loop will be constant, so current will be zero. And when it comes out, field lines through the loop will decrease, again current is being produced. So we say when the loop goes in, so we say for how much time current is being produced, we say, sir, listen to me very carefully, we say velocity is equal to distance upon time, and time is equal to distance upon velocity. And distance, for how much distance, we say flux was changing. Sir, we say over here, when it was going inside, when it has covered this b distance, when it crossed this b distance, so we say till then, we say flux was changed, and till then current was being produced. We say, sir, this T1 is equal to, this is B divided by, and it is moving with the velocity V, B by V. And this is the time when current is basically being produced over here. And when it comes out, again, when it comes out, we say on coming out, we say I is also produced. So in that case, let's call this as T1, that T2 will be again B divided by V. So total time, for how much, for the time the current is being produced, sir, total time will be T1 plus T2, that is 2B divided by V. That is 2B divided by V. Is that clear, guys? Is this clear, guys? I just need to know in the live chat. Is this clear? Is this clear? This is bit difficult. This is bit difficult to make you understand over here. Let me know. Give me a signal in the live chat with the fire emojis if this is clear. Is this clear, guys? This is also the question. In this particular case, listen to me very carefully. Over here, it was A is greater than B. And this is the question where A is less than B. B is this distance, A is the width. This is your homework. Okay. Now let's move on to this one. Convert the flux time graph into the EMF time graph. Listen to me very carefully. This is the flux and this is time. The flux time graph. As we know, listen to me very carefully. When it comes to the EMF, we say, sir, EMF is equal to minus d phi divided by dt. Sir, according to the Faraday's law, EMF is d phi by dt. Listen to me very, very, very carefully over here. Listen to me very, very, very carefully over here. So EMF is equal to minus d phi by dt. Sir, what is this d phi? Phi is this y-axis, time, t is time axis. We say, let's suppose I have, this is y-axis and this is x-axis. And we say this is the graph over here, a straight line. And in this case, if I just tell you, could you please tell me the slope? You say, sir, slope will be simply, sir, that is tan of theta or we say perpendicular by base, that is dy divided by dx. So slope is always perpendicular divided by base, that is dy by dx, or you say delta y by delta x, or you say y by x, one and the same thing. Okay, now you tell me one thing, sir, in case of flux time graph, what is slope? That is d phi by dt. In case of y versus x graph, what is slope? Delta dy by dx. Over here, slope is dy d phi by dt. So what is d phi? D phi by dt is EMF. As here slope in case of we say flux time graph. Sir, we say when it comes to the slope is nothing but we say d phi divided by dt, that is perpendicular divided by base. Yes, sir, this is the slope. Now listen to me very carefully. Sir, d phi by dt is EMF. Now, can we say from equation first and second, so this EMF is equal to, this is negative sign, instead of d phi by dt, we write slope. This is slope. Yes, sir. 110% we can write it something like this. Now, if this is the slope over here, yes, sir. Slope is equal, EMF is equal to negative of slope. Now see. Always remember, sir, this increasing graph, if theta is less than 90, its slope is always positive. Its slope is positive. Okay. And this is a constant graph. Its slope is always constant. This is constant, positive constant. And this line, it has the slope 0. It has slope 0. Why? Because this is parallel to the x-axis. And this line has got slope as negative. Why? Because this is a decreasing graph. Theta is greater than 90 degrees. So, and slope over here is also constant. So, in the flux time graph, from this point to this point, slope is positive and is constant. From this point to this point, we say slope is 0. From this point to this point, we say slope is negative and this is constant. Slope is negative and this is constant. Now, my dear people, listen to me very carefully over here. If I have to make the graph between EMF, okay, so we say, sir, from this point to this point, slope is negative, means EMF is negative and constant. What does this mean? This means EMF is negative, because from flux time graph, slope means EMF. So EMF is positive and constant. From this point to this point, EMF is, we say, 0. Now let me make the graph over here only. See, on this axis, we have the EMF. On this axis, we have the time. Okay. See, my dear people, if, sir, from this point to this point, slope is positive, okay? And we say when it comes to the EMF, sir, EMF means over here this one. EMF is negative of slope, so EMF is negative. Sorry, okay? Because this is negative of slope. If you place the slope is positive, place positive over here, negative into positive is negative. So slope is negative. And over here, EMF is negative, and over here, EMF is positive. From this point to this point, EMF is positive. Why? Because slope is negative. Negative of negative is positive. So we say, sir, first EMF is negative and is constant, graph will be something like this. Then, sir, EMF over here is 0 because slope is 0. Then it will be something like this. EMF is 0 from this point to this point. Then from this point to this point, EMF is positive. So, and is constant. EMF is positive. Is this clear, guys? First, let me know, is this clear? See, from A to B, slope is positive. And how to find EMF? EMF is negative of slope. If this is negative, slope is positive. Negative into positive is negative. Is this clear? Guys? Is this clear? Is this clear, guys? Okay, let's move on to the next question. This is the next question we have over here. In this particular case, find the induced EMF in the circular loop where R is much less than this one. You have the wire. In this wire, current is flowing I naught into T square. This is infinitely long wire. And you have got a loop over here. Okay. And you guys are supposed to tell me how much is the EMF induced in the loop. Okay. See, to find the EMF induced in the loop, to find the EMF induced in the loop, listen to me very carefully. We have to find the EMF induced in this particular loop. Sir, when it comes to the EMF, we say EMF is equal to, that is minus d phi divided by dt. According to the Faraday's law, EMF is d phi by dt. Now the question over here is, we say, sir, when it comes to the d phi by dt, we say, sir, d by dt of, sir, flux phi. Phi is what? We say, sir, magnetic field into area, that is B into A. That is B into A, magnetic field into area. I'll give you the break at exactly at 8:30. 8:30 will be the break, okay? You have to finish this first, guys, okay? NEET is very near. Where do you guys want break? We'll give you the break at 8:30 exactly. Is that cool? So we say EMF is equal to minus d phi by dt, and d by dt of what is flux? Flux is equal to a magnetic field into area, B into A. Now the question over here is, we know the area of loop, area is equal to pi into r square. And how much is the magnetic field through the loop? Sir, because of this wire in which current I is flowing, magnetic field at r distance will be how much? This wire is creating the magnetic field over here. And that field is crossing the loop. And that field is variable. Because of that field, changing field or changing flux, EMF is being produced. Now see, my dear people, we say, sir, magnetic field B due to infinite wire. How much is that? We say, sir, B is equal to mu naught I divided by 2 pi into this R. If this is at R distance. Magnetic field due to an infinite wire at R distance is mu naught I divided by 2 pi R. Now, my dear people over here, what is the value of current? That is I naught into T square. So we can write this as mu naught. And then we have, sir, I naught, mu naught I naught into T square divided by, we say, 2 pi into R. Now put the value of this over here and put the area over here also. So we can further write this, magnetic field is equal to, we say, mu naught I divided by 2 pi into R. Mu naught into I naught into T square, mu naught I naught into T square upon. We have to write this. We say, sir, EMF is equal to, that is minus d by dt of. Instead of B, we can write, sir, mu naught I naught into T square upon, we say, sir, 2 pi into capital R, and into area. What is the value of area? That is, we say, pi into R square. And then if I just write it over here, sir, this EMF will be simply, that is minus. Sir, take the mu naught out, I naught out, okay? And what is constant? Pi out, R square out. Okay, and this pi will get cancelled out. So this is mu naught into I naught. And we say, sir, this R square. Okay, and divided by 2R. And what remains over here? D of T square divided by dt. dt square divided by dt. differentiation of t square with respect to t. So you can say over here EMF will be simply minus mu naught into I naught into r square, and differentiation of t square with respect to t is 2t only. Okay, divided by, we said 2r. This 2 and 2 we can cancel out over here. What remains is EMF is equal to minus mu naught into I naught into r square into t divided by this r, divided by this r. Is this clear? Is this clear? Is this clear? This is the value of magnetic field in this particular case. Is this clear to every one of you? Everyone means everyone. I just need to know if everybody is able to understand these points. Is it clear, guys? Okay, great. Now, let's move on to the next one. Let's move on to this one. Let's move on to this one. A circular ring of radius r is placed in a magnetic field B is equal to B naught into T square. Is varying with time. Find the induced EMF at T is equal to 2 seconds. We have a ring over here and it is placed in a magnetic field B is equal to B naught into T square. Okay. So it's a varying, changing magnetic field. The radius of the ring is r. We have to find the induced EMF in the coil. See, when it comes to the EMF, we say, sir, EMF is equal to minus d phi divided by dt. Okay. So we say, sir, EMF over here, I can write minus d by dt of, and when it comes to this, it is B into A, magnetic field into area. So we say, sir, this EMF would be simply, that is equal to minus, and we say d by dt of, sir, when it comes to the magnetic field, that is B naught into T square. Okay. And over here, I can write area. Area of this ring is pi into capital R square. So we can say, sir, this EMF will be simply minus, and take this B naught out, it is constant, pi out, it is constant, R out, it is constant. We say, sir, B naught into pi into R square, B naught pi into R square, B naught pi into R square. Then we say dt square divided by dt. Okay. So this EMF is equal to minus. We say, sir, this is B naught. And then we have this pi. And then we have this R square. And then we say, sir, 2t. Differentiation of dt, t square is 2t. And if we just write over here, sir, this EMF is equal to, that is minus. We say, sir, we are supposed to find the EMF at t is equal to 2 seconds. Put the value of t is equal to over here. That is B naught into pi into R square. 2 into 2 is 4. That is 4. This is the answer over here. Is this clear, guys? Is this clear to each and everyone? Is this clear to each and everyone over here? Let me know in the live chat, guys. Is this clear to each and everyone? All the people out there, make sure you like this particular session over here only. This is the EMF over here. Next question. Okay, we have the motional electromotive force. Listen to me very carefully. I'll make you understand this in just 5 to 7 minutes. What does motional EMF actually mean? Let's suppose we have a magnetic field over here. We have a magnetic field over here. This is the inward magnetic field. Okay. Cool. This is the magnetic field which is over here. And this is the magnetic field B. And this is inward. This is inward. Okay. Magnetic field is present in this particular region over here. Yes, sir. Now, I say I have a rod. I have a rod. This is a rod which I have placed over here in this one. This is a rod. Okay. This is a rod. This is a rod which is placed in this magnetic field. Listen to me very carefully. This is a rod, or we say conductor. And in this conductor, we have basically electrons. We have electrons. Listen to me very carefully. We have charge. Let's suppose this conductor carries the charge. This is the charge inside this rod. Okay. Now, we say the length of the rod is, let's suppose, L. The length of the rod is L. And it is moving with the velocity V inside this magnetic field. It is moving with the velocity V inside this magnetic field. It is moving with the velocity V inside this magnetic field. Okay. Now, when it moves with the velocity V inside the magnetic field, and this rod contains the charge because it's a conductor, so it is like charge is moving inside this magnetic field. We say here, rod is moving. Rod is moving inside the magnetic field. So charge inside the rod is also moving. Charge inside the rod is also moving. Charge inside the rod is also moving. Okay. So we know whenever the charge moves inside the magnetic field, force acts on it. That's what we call the magnetic force. So magnetic force acts on the charge. So we know magnetic force acts on the charge whenever the charge moves inside the magnetic field. And when it comes to that magnetic force, that is equal to FB, magnetic force, it is equal to, that is QVB sine of theta, where theta is the angle between magnetic field and velocity. Magnetic field is inward, velocity is forward, that is 90. So angle is 90 over here, that is QVB. This is the magnetic force. And what is the direction of this magnetic field force? Sir, place your fingers along the direction of velocity, curl it towards the magnetic field. Velocity is forward, curl it towards magnetic field, that is inward. Thumb is pointing upward. We say thumb is pointing in the upward direction. So after some time, when the rod reaches over here, we say, sir, on this charge, force acts, and this force will be in upward direction. And if this force is in the upward direction, my dear people, we say after some time, the charge, this positive charge is accumulated at the top of the rod. And if positive charge is accumulated at the top, we say negative charge will be accumulated at the bottom. Okay, if the positive charge will go on the top of the rod, negative charge will be occupied obviously at the bottom of the rod, because force on positive charge is upward, force on negative charge will be obviously in the downward direction. Now, you tell me one thing. So, we say when positive charge is at the top, negative charge is at the bottom, charge separation takes place. Okay, charge separation takes place. And whenever the charge is separated, my dear people, so we say in that particular case, electric field is being set up. Okay, from positive charge to negative charge, electric field is set up from we say positive to negative charge. We say electric field is being set up from positive charge to negative charge in that particular case. Now, if the electric field is set up from positive charge to negative charge, now listen to me very carefully. On the rest of the charge which is over here, on the rest of the charge, now two forces will act. First one is the magnetic force that we know, and second one is the electric force that because of this electric field. Now, sir, because of the magnetic field, magnetic force is acting. Now, when electric field is developed, because of this electric field, electric force is also developing. Okay. Now, because of electric field, we say F electric also acts on the charge. Okay. F electric acts on the charge. Now, my dear people, so acts after some time, we say, sir, when both the forces acts on the charge, we say these two forces after some time will be equal. So we say this F electrostatic force will be equal to the magnetic force after some time. What I'm trying to say is that when a rod moves in a magnetic field, sir, charge separation takes place. Positive charge is at top, negative charge is at bottom. Electric field is set up. Now two forces will act, electrostatic force and magnetic force. Both will be equal after some time. Okay. Both will be equal after some time. And when it comes to this electrostatic force, we know, sir, it is equal to Q into E. What is the value of electrostatic force? Q into E is equal to, what is the value of magnetic force? We just studied QVB. And we say this and this will get cancelled out over here. This is electric field. This is velocity. This is magnetic field. We can write electric field as potential difference, as we know. Let me just write over here as electric field is equal to potential difference upon, or you just write directly over here. Electric field is equal to, we say EMF, or potential difference upon length, where L is the length of the rod. This is the formula for electric field. This I have told you before also. So we say, sir, instead of this electric field, I say EMF divided by L is equal to V into B. So we say this EMF is equal to BL and this V. BL and this V. Okay, BL and this V. So my dear friends, what I'm trying to say, whenever you have a conductor or a rod which is moving inside a magnetic field with some velocity, we say EMF is being induced in that rod, and that EMF is what is called motional electromotive force, EMF. This EMF is being produced because of the motion of the rod. That's why we say it is motional EMF. So whenever the rod moves inside the magnetic field, with some velocity, EMF is being induced in that rod, and it is called motional EMF. It is called motional EMF. Why it is called motional EMF? Because it is due to the motion of the rod. It is due to the motion of the rod. Is that clear, my dear people? Who are these lovebirds in the live chat? Last time also I told you, I warned you not to make this as a dating app. Huh? You guys come to teach, come to learn over here. This motional EMF. Everybody, is that clear? Is it clear, guys? Let me know with the fire emojis if this is clear. Whenever the rod moves inside a magnetic field, okay, we say EMF is being induced in that rod, and that EMF is called BLV. Okay, so we say, let's suppose from now onwards, if someone says you have a magnetic field over here, and you have a rod which is placed in that magnetic field which moves with some velocity v, it has length L. So what happens to this rod? We say EMF is being induced. That EMF is called BLV. B is the magnetic field, L is the length, V is the velocity. Okay, that's cool. That's great and cool. Great. Now, we have the case 1 over here. Listen to me very carefully. Sir, listen to me very carefully. Sir, over here, in this particular case, when magnetic field and velocity are parallel, like over here, magnetic field is in the forward direction, you have placed a rod, and this rod also moves in the same direction. In this case, magnetic field and velocity are parallel. See, when we talk about this rod, in this rod we have the charge. Let's talk about force on the charge. Force F is equal to QVB sine of theta. Okay, theta is the angle between velocity and magnetic field. We say, sir, over here theta is equal to 0 degrees. If magnetic field and velocity are parallel, in that case, velocity and magnetic field are having the theta is equal to 0 degrees angle between them. And we say F is equal to QVB sine 0. So magnetic force in that case will be 0. Magnetic force in that case will be 0. F is equal to QVB sine theta, and magnetic force in that case would be 0. Okay. If magnetic force is 0, my dear people, listen to me very carefully. If magnetic force is 0, you tell me one thing, will the charge separation take place? No, sir. Will the charge separation take place? Will this charge go at the top? No, sir. Why? Because no force is acting on the charge. So we say if the charge separation will not take place, we say electric field will not set up over here. If electric field will not set up over here, my dear people, we say no EMF is being induced in the rod. Electric field is 0, EMF is 0. Electric field is 0, EMF is 0. So in that case, EMF will be 0. So charge separation will not take place. Okay. So in that case, we say EMF will be 0. No EMF is produced when magnetic field and velocity are parallel. We say in that case, EMF will be 0. Okay. All the three should be mutually perpendicular actually. See, in this case, why charge separation took place? We say, sir, magnetic field is inward, velocity is forward, and length is in this direction, vertically. So we say all the three are mutually perpendicular. Now let's talk about the case 2. Over here, we say velocity and length are parallel. Here, when we say velocity and length are parallel. Okay. Let's talk about how much is the EMF in this case. We say over here also EMF is equal to 0. When any of the two are parallel, in that case EMF is 0. Why, sir? See. Let's suppose this is the charge inside the rod. Can you tell me how much is the magnetic force on the charge? Sir, magnetic force will be Q into V cross B. What is the value of force? F is equal to Q into V cross B, or QVB sine theta. Okay. But if you have to find the direction of magnetic force, place your fingers along the direction of velocity, curl towards magnetic field, it is upward. So if we have this rod, sir, this rod is thin. Is it possible that charge separation would take place in this very little space? Do you think that positive and negative charge will be separated in this very little place? No, we say here charge separation is not possible in breadth of the rod, or width of the rod. Charge separation is only possible in the length of the rod, but in the width of the rod it is not possible. So we say in that case EMF will be 0. If charge separation is not there, so how EMF will be there? So EMF in that case will be 0. Now in this case we say when magnetic field and length is along this, magnetic field is also along x-axis, and magnetic field and length are parallel. In this case also EMF is 0. Why? Because here also if you have this charge, can you tell me the magnetic direction of magnetic force on the charge? Place your fingers along the direction of velocity. Curl towards the magnetic field. Sir, something like this. Magnetic field is inwards. That is in the width of the rod only. Let's suppose this is a rod in the width of the rod only. So here also charge separation is not possible. So EMF will be 0. So I'll write a statement. When any of the two among B, L, V, when any of the two among B, L, V is parallel, then EMF in that case is 0. Then EMF in that case is 0. Any of the two are parallel. We say all the three should be mutually perpendicular. All the three should be mutually perpendicular. All the three should be or must be mutually perpendicular, my dear people. I hope this is clear to each and everyone. I hope this is clear to each and everyone. Okay. Let's move on to this one. Let's move on to this one. We are supposed to find in this particular case, find EMF. We have to find EMF over here. We have to find EMF over here. See, we have a rod L. We have a rod. Its length is L. And it is moving with a velocity V in the forward direction. We have to find EMF. We know, sir, whenever the rod moves in a magnetic field, we say EMF is being induced in that rod, provided all the three, that is magnetic field, velocity and length, should be mutually perpendicular. Now see over here, if this is rod, it's having length L, this is 60 degree. Can I say this is, we say L cos of 60 degrees, and this one we say over here, this one we say over here, this is L, this is, we say L sine of 60 over here. This is L cos 60, this is L sine 60. Okay. Now, in this particular case, this is L. Sir, because of this length, magnetic field EMF would be 0. Why? Because this length and velocity are parallel. So the two should not be parallel. So this is the length, this is velocity, magnetic field is outward, all the three are parallel or perpendicular. So we say in this case, if you have to write, you say, sir, B, V, and instead of L, you say L sine of 60 degrees. Is that clear? We don't have to take over here. We don't have to take over here in this particular case cos 60, but we have to take L sine 60. Put the value of sine 60 over here. That is the answer. Now, can you tell me the answer of this particular question? Let's suppose you have got a magnetic field. You have got a magnetic field. This magnetic field. Okay. This is the inward magnetic field. And in this case, I say, you have got a rod something like this. You have got a rod something like this. Okay. You have got a rod something like this. Cool. This rod is something like this. And this angle is given as, we say 60 degrees. This angle is given as 60 degrees over here. And this is L. This is over here L. And this structure, angular structure, it is moving with a velocity V. And this magnetic field is B. You guys are supposed to tell me in this particular case, how much is the EMF which is being induced? This structure is something like this. This is L, this is L. Angle between these two is 60 degrees. And we say over here, sir, it is moving with a velocity v. Magnetic field is B. How much is the EMF? Sir, in this case, if we talk about the EMF, we say, sir, BV. And you have to take the effective length over here. Don't say, sir, 2L. No. You have to take the effective length. And what is effective length? Effective length is this much. Effective length is this much. Okay. This is what we call L effective. L effective is this much. So we say, my dear people, this EMF is equal to magnetic field is B. We say velocity is V. And L effective in this case will be L only. If this is L, this is L, this will be L only. This will be 60, this will be 60, this will be 60. So this will be L. So BVL will be basically the net EMF in this case. Is this clear? Effective length of this one. That is, join one end with the another end, you will get the effective length. Can you tell me the answer of this question? Let's suppose you have this magnetic field over here. You have this magnetic field. This is inward magnetic field. And in this inward magnetic field, if I say you have just a second. Yes. You guys are supposed to tell me this is given as, this is the radius R over here, and it is moving with the velocity V. Magnetic field is B. Can you tell me how much? I have made it over here. This is the magnetic field. This is the semicircular ring, radius R. It is moving with the velocity V. How much is the magnetic field being produced over here? How much is the how much is the EMF which is being produced over here? Can you tell me in the live chat how much is the EMF which is being produced over here? In the live chat, everybody of you. How much is the EMF which is being produced over here? See, sir, when it comes to the EMF, listen to me very carefully. Sir, when it comes to the EMF, we say EMF is B, V, and if you have a straight conductor, then you take the L length. When you have something like this curved or you have some angular shape, in that case, take the effective length. Sir, BVL effective. What is effective length? Join one end with the another end. That is what we call the effective length. And how much is L effective in this case? Sir, L effective in this case is R plus R, that is 2R. That is 2R. So we say this EMF is equal to, that is BV. L effective is nothing but 2R. BV 2R is the correct answer in this case. And if I ask you, which one is at higher potential? Sir, EMF means potential difference. Okay. Which one is at higher potential? And which one is at lower potential? Let's suppose you have got the rod over here. You have got the rod over here. This is the rod. If I say positive charge is accumulated at the top, negative charge is accumulated at the bottom. So which end is at the higher potential? We say this is at higher potential and this is at lower potential. So positive charge means higher potential. In this case, if I say you have to tell me which end is at the higher potential. Let's suppose this is P and let's suppose this is Q. Okay. M and Q. This is M and that one is Q. Sir, if you place your thumb along the direction of velocity, curl it towards the magnetic field, thumb is pointing towards right. Sir, see, this is a wire. This is a current carrying wire. In this wire, charge is present. Can you tell me what is the direction of the force, magnetic force, which acts on the charge? Sir, Q into V cross B. Place your thumb along the direction of current, curl it towards magnetic field, thumb is pointing towards right. So in this one, positive charge will be accumulated at Q, negative charge will be accumulated at M. So Q is at higher potential. So answer is this one. Q is at higher potential And if I ask you in this particular case, which one is at higher potential? Let's call this as X and let's call this as Y. How to find it? You have to find the direction of force on positive charge. Sir, this one is the velocity. Inward is the magnetic field. V cross B, Q into V cross B. Thumb is pointing in the upward direction. So means positive charge will be accumulated over here, negative charge over here. So this one is at higher potential. Is that clear, guys? Is that clear? Now you have to tell me the answer of this particular question. You have to tell me the answer of this particular question. You guys have to tell me the answer of this particular question over here. Okay, see, it is something like this. Circuit is something like this. You have got a resistance, okay, and it is something like this. And you have got a rod over here. This is a rod. I'll make it. This is a rod, something like this. This is a rod, something like this. Okay, this is a rod, something like this. And this rod is basically movable. It is moving with a velocity v. It is moving with a velocity v. And the radius is r. It is moving with a velocity v. Okay. And in this case, magnetic field is inward. In this case, magnetic field is inward. You have to tell me over here, how much is the power? Find power in the circuit. Find power in the circuit. Find power in the circuit. You have a resistor and then you have a movable rod. This rod is moving with a velocity v. And this velocity is given as 20 meters per second. And magnetic field in this case is 1 Tesla. And the length of the rod L is equal to 1 meter. The length of the rod is 1 meter. And in this particular case, you guys are supposed to tell me the power in the circuit. You guys are supposed to tell me the power in the circuit. You guys are supposed to tell me the power in the circuit. See, let me just tell you, sir, when it comes to the power, we say power is V square divided by R. Power is V square divided by R. And when it comes to this V, what is V? V is the potential difference. We know the formula for power is V square by R. What V means potential difference, and that is EMF. Sir, EMF square divided by R. And when it comes to the EMF, listen to me very carefully. You have a rod over here. This rod is having the velocity V. It is moving inside the magnetic field B. It is having the length L. Sir, we know EMF is equal to B, L and V divided by R. It's square, square, square. And I can write it something like this. What is the value of magnetic field? That is 1 Tesla. What is the value of length? That is 1 into. What is the value of velocity? That is 20. 20 square is 400. And what is the value of resistance? And in this case, resistance is given as 0.2 ohm. Sir, R is given as over here 0.2 ohm. So I can write this as 2 divided by 10. 0.2 is also 2 by 10. And this will be how much? That is 4000 by 2. That is 2000. So power in this case is nothing but 2000. That is power is nothing but 2 kilowatt. Okay. Option 4. Option 4. Is that clear? Is that clear, my dear people? And make sure you like this session if you have not liked this session. And what is the value? What is the value of EMF in this particular case? Can you tell me the value of EMF? Option A, this is the magnetic field is inward, velocity is forward, and this is the radius. Option A is BV2R. Option B is BVR. Option C is 0. Option D is BV4R. Which one? Which one? Which one? Which one is the correct option in this case? What is the correct option over here? A, B, C, D. A, B, C, D. Which option is correct? Which option over here is correct? Which option over here is correct? Can you tell me in the live chat? Option C is the correct. Why are you marking the option A, guys? See, I told you, in this case, you have to see, sir, EMF is equal to BVL effective. I know, sir, when it comes to the effective length, that is join one end with the another end, that is R plus R. In this case, L effective is 2R. In this case, L effective is 2R. Okay. Now, this L effective, don't you think this L effective and V are parallel to each other here? We say V and L effective are parallel. When any of the two is parallel, we say in that case EMF is 0. So EMF in that case is 0. This is the first statement that I told you, guys. Next one, overshare. This is a good question, actually, important. Mark it important. See, we say, sir, magnetic field, you have a square loop. You have a square loop. This square loop is made up of 4 wires. This square loop is made up of 4 wires. This one, this one, this one, and this one. 4 wires. And it is moving. It is moving with the velocity. It is moving with the velocity V. It is made up of 4 wires. It is moving with the velocity V. And you guys are supposed to tell me, find the induced EMF in the square loop between A and B, in this rod A and B, in BD. So if I say solution over here, sir, when it comes to the EMF, EMF in AB is 0. We say EMF over here, AB is 0. Why, sir? Because the length of AB is parallel to velocity. So it will be 0. And when it comes to, sir, EMF of this one, that is CD. EMF of CD. EMF of CD is also 0. Why? Because it is also parallel. It is also parallel to velocity. When any of the two is parallel, EMF is 0. So what remains? AB and we say BD. Now what is the, let's suppose the length is L and this length is also L because this is a square loop. EMF in this is nothing but, listen to me very carefully. We say EMF in AC is basically BV into L. Magnetic field is outward. Length, velocity is forward. And we say EMF in case of this one, that is BD, is also BV into L. Now, if I have to make it circuit, let's make it circuit. Let me just show you over here. Let's make the circuit. Let me show you how do I make the circuit. Listen to me very carefully. It is important. Sir, over here, sir, EMF is BVL. Can you tell me, sir, where will be the higher potential, from higher side or lower side? See, guys, in case of battery, you say, sir, this is the battery which is something like this. Okay. And this is the higher potential of the battery, this longer one. The shorter one is the lower potential of the battery. And it is written over here 20 volts. What is meant by 20 volts? We say, sir, this 20 volts is nothing but EMF. This means EMF. EMF is 20 volts over here. If I say 30 volts, EMF is 30 volts. If I say 40 volts, EMF is 40 volts. This is higher potential or positive terminal, negative terminal. This you have seen. Now, if over here, my dear people, potential difference is being created over here. Okay, one more thing I just need to tell you. If we say, sir, we have a magnetic field over here, and inside this magnetic field, you place a rod, it is moving with a velocity v, this is b, and length is l. We say EMF is being produced over here. Sir, that EMF is BLV. What is this EMF? The potential difference. And you can say, sir, this rod has EMF. Means this rod behaves like a battery. Because battery only has EMF. So, positive charge is at top, negative charge is at bottom. So, it would be something like this. Sir, higher potential from the upper side, lower potential from the lower side. So this will be the battery of this rod. If you have to make it like a battery, higher potential from higher side, lower potential from lower side. Now over here in this case, sir, if we say velocity is in this direction, magnetic field is outward. Sir, curl your fingers from velocity to magnetic field. Force on positive charge, V cross B. Force on positive charge in the downward direction. So we say this is positive and this is negative. If you have to make the battery instead of this, that would be something like this. Positive from the lower side, negative from the upper side. This is positive and this is negative, higher and lower. This is point A and this is point B. And if EMF in this case is 0, so it behaves like a simple wire. So this is a simple wire. Now come over here. When it comes to this rod, sir, same over here, V cross B, thumb is downward, so force on negative charge is downward, so this force on positive charge is downward, this is positive, and this would be in that case the negative terminal. So what is the value of EMF of this battery? That is BLV, and this is also BLV. Okay, this is BLV and this is also BLV. And if I ask you to tell me, what is the net EMF in the complete loop? Listen to me very carefully, my dear people. Important thing I just need to tell you. That is EMF in the complete loop. Let's suppose this is the battery, something like this. This is one more battery, something like this. This is BLV, BVL, or this is BVL. This is the EMF, this is EMF. Like you have 20 volts, similarly BLV, BLV. Let's suppose this is the point, this is point A, this is point A, okay? Let's start from the point A. Let's start, let's start from the point A. This technique I have shown you in the current electricity. Let's start from the point A. If I have to find the potential difference in a closed loop, to find we say potential difference in a closed loop. See, how do we find a potential difference in a closed loop? Let's start from point A. If we start from point A, let's move in this direction. VA, then over here, you are moving from lower potential to higher, from lower to higher. Whenever you move from lower to higher, guys, remember, I told you take this as we say positive, that is BLV. Remember in current electricity, I said, sir, if this is, we say 20 volts, this is point A and this is point B. If you move from A to B, you were saying that, sir, VA, and then from higher to lower, it was minus 20 is equal to, we say, sir, VB. I hope you remember this, my dear people. Same is the case over here. From VA, if you are moving something like this, lower to higher, it is positive. And in this battery, you are moving from higher to lower, then it is negative BLV. And again, you are moving in a closed loop, you are reaching the same point, A is equal to VA. And in this case, you can say it is nothing but a 0. Net EMF in this case is basically, we say 0. Because EMF in the complete loop or the closed loop is 0. Is this clear, guys? Is this clear, guys? Is this clear to each and everyone? Okay. Let's move on to this one, this question. Okay, this is the question we have over here. The question is something like this. You have the magnetic field, you have the magnetic field, you have the magnetic field. Okay. And in this magnetic field, you have a structure something like this. You have a structure something like this. Listen to me very carefully. Listen to me very carefully. Listen to me very carefully. You have a structure something like this. So this is the structure and this is the structure. Okay. This radius is basically R and this radius is basically 2R. Okay. And you guys are supposed to tell me the EMF produced in this case. Okay. And this structure is basically moving with the velocity V in the magnetic field B. Now see, let's suppose this is the point A and this is the point B over here. One thing I just need to tell you. First thing, sir, we have to find the EMF produced in this entire structure. See, you have got, this is the first structure over here. You have got, this is the first structure over here. This is the first structure over here. This is the first structure. And this is the another structure over here. This is the second rod, okay, which is semicircular wire. This is a semicircular wire. You have got this first structure and you have got this second structure. Now, in this case, we say, sir, EMF will be because of the first structure. EMF will be because of the second structure separately. Because this is also a conductor, this is also a conductor. We say, let's call this as 1, let's call this as 2. When we talk about the EMF over here, sir, EMF because of this is EMF is equal to BV. And we know whenever you have a curved shape, angular shape, in that case, you take the effective length. And how much is the effective length, sir? The radius is basically, this is 2R because the radius of bigger one is 2R. From this point to this point, radius is 2R. From this point to this point, radius is 2R. So 2R plus 2R is 4R. So that will be 4R, PV 4R. Now, sir, EMF of this is the first one. And when it comes to, sir, EMF of second one, EM of this second structure, that is how much? We say, sir, magnetic field is B, velocity is V, and effective length of this semicircular ring is how much? That is also join one end with the another end. This one, that is also 2R, PV2R. Is that clear, guys? Is that clear, guys? Is that clear? You understood this, what I'm trying to say over here? You understood this, what I'm trying to say over here? This structure has separately, this structure has separately. Okay. Now, if you have to make it, if you have to make the battery, so battery will be something like this. I'll make it over here. See, let's talk about the direction of force on positive charge. Velocity is in the forward direction. Curl your fingers from V to B. Thumb is pointing in the downward direction. So positive charge is accumulated at the bottom. So because of the first one, I'll make it over here. Because of the first one. So this will be because of the first one. Positive charge is accumulated at the bottom. This will be, and this is BV4R. And because of this one also, sir, positive charge is accumulated at the bottom. So this is the battery because of the second one. So this is also BV4R. And this will be the loop. This will be the loop. Now let's move on to this one. Let's move on to this one. In this case, can you tell me what is the value of magnetic field, EMF? Sir, EMF because of this is 0. Why? Because this is parallel to velocity. EMF because of this is also 0. Why? Because this is also parallel to velocity. EMF will be because of this only. So we say EMF in this case is BV into L. That is because of this one only. You have got the next one. Okay, this one. See, magnetic field is B and velocity is sir V. Velocity is sir V. Okay. And in this particular case, you have to basically say, when it comes to sir EMF, you say that is nothing but BL and V. And most importantly, BVL effective, L effective. Now, sir, when it comes to this one, see, when it comes to the effective length, join one end with the another end and that will give you the effective length. This is L effective. And my dear people, if the radius of this ring, if this radius is R, this is R. And you should know that over here. See, if this is, we say R, and we say this is, we say R, their resultant, this one is basically how much this one will be exactly R. Okay. Sorry, this one will be root 2R. Okay. Because angle is 90 over here. This angle is 90. If you have a vector something like this, this is 90 degrees. If this is F, resultant will be root 2F. Similarly, over here, if this is R, this L effective will be how much? Root 2 of R. Okay. Now it is something like this. Listen to me very carefully. I'll make you understand. This is the magnetic field. 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 Okay. And now forget about this one. We took its effective length and effective length is this one. And that is L effective. L effective is, I'll just write directly. We say root 2 into R. My dear people, this is it. And it is moving with a velocity. V. Now see, sir, this root 2R will have two components. Which one? Sir, this one. And we say, sir, this one. This is root 2R. And if this is root 2R, this is R and this will be R. Because I told you, if this is root 2R, this distance will be R and this distance will be also R. Sorry, this component will be R, this component will be R, and this is root 2R. If the angle is 90. So, sir, if you join this point with this point, this will be L effective and this is root 2R. And if you make its two components, one will be R, another will be R. Now, sir, this R and velocity is parallel. So we cannot take this R. When it comes to the EMF, we say, sir, BV. And L effective in this case is this R. So we say BVR. So EMF will be BVR in this case. Is that clear? Let me know in the live chat. Is that clear? Let me know in the live chat. Everybody. Is this question clear, guys? Let me know in the live chat, everybody of you. Is that clear, guys? Yes, yes, yes. We'll give the break. We'll finish these questions. Okay. 4 to 5 questions we'll finish and I'll give you the break. Okay. I'll give you the break. Is this clear, guys? See, you have got this over here. Listen to me very carefully. This is a structure. This rod has got length L. This rod has got length L. Okay, this is length L. This is length L. And this structure is moving with the velocity v. This structure is moving with the velocity v. And you have got the magnetic field over here, which is in the outward direction. And this structure, angular structure, is having the angle between them 120 degrees. And it is moving with a velocity v. We know whenever the rod moves inside a magnetic field, we know EMF is being induced. Now the question here is find the EMF induced in the structure. Find the EMF induced in the structure. You guys are supposed to tell me EMF induced in this structure over here. Now see, sir, we know when it comes to the EMF, sir, we say this EMF is nothing but, we say BVL effective. Because in case of the angular structures, curved structures, we take the effective length. And how to find the effective length over here? My dear people, I can just tell you, when it comes to the effective length, you can simply say join one end with the another end, and this is what we call L effective over here. Okay, this one is what we call L effective. Now if I say over here, my dear people, if I say, sir, this L, can I say this will be its horizontal component? Yes, sir. And this will be its vertical component. Yes, sir. This will be its vertical component. Okay. And this is 120. Over here, sir, this is 60. This is 60. So we say this one will be, we say L cos of 60. And this vertical component will be simply L sine of 60. Because total is 120. This angle is 60. So this is L cos 60, L sine 60. And this is also L. This will be over here L cos 60 once again. One of its component is L cos of 60. And another component over here is L sine of 60. Now, my dear people, this L sine 60 and L sine 60 is exactly like this length, okay? So this is L sine 60 plus L sine 60 is 2L sine 60. Means this length is nothing but 2L sine of 60. Means the effective length of this structure is 2L sine 60 over here. So if we have to write the EMF, we say EMF is equal to BV, and instead of L effective, we say 2L sine of 60 over here. 2L sine of 60 over here. So we say, my dear friends, we say EMF will be simply BV. Instead of this, see, we say, sir, this is BV. And then you have 2L. Sine 60 is root 3 divided by 2. 2 and 2 will get cancelled. That is root 3 BVL. Root 3 BVL. This is EMF. This is root 3 BVL. This is EMF. Okay. Next question we have over here, this one. Let's talk about this one. Find the current in the rod. Find the current in the rod. See, you have this rod, okay? It is moving with a velocity v. Its length is L. And over here, you guys are supposed to tell me the current in the rod. And it is placed in a magnetic field B. It is placed in a magnetic field B. Now see, this rod is basically placed in a magnetic field B. It is moving with a velocity v. So can you tell me how much is the EMF in the rod? EMF is equal to, sir, BLV. Simply, B is the magnetic field, V is the velocity, L is the length. Now, over here, listen to me very carefully. This rod now behaves like a battery. as the rod has EMF, as the rod has EMF, so it behaves like a battery. So it behaves like a battery. As the rod has EMF, so it behaves like a battery. Now I can redraw the structure over here. So instead of this rod, I'll make the battery. How to make the battery of the rod, sir? It will be, you have to see the direction of positive charge. Sir, V into B, V cross B, Q into V cross B. Curl your fingers from velocity to magnetic field. Thumb is pointing in the upward direction. Means positive charge is at top, negative charge is at bottom. So instead of this, if I have to make the battery, we say positive charges from the upper side, negative charges from the lower side. Okay? And I'll basically make it from the another side. There is no problem in that. If I interchange the position of this rod and this one. So do we have got this resistance over here? And we have got this resistance over here. This is R and this is R. And we have over here, this is nothing but BLV. This is EMF. Now, my dear people, this is the battery. You have got two resistors and we have to find the current. We know, sir, as V is equal to I into R. Now, I can write over here, I is equal to V divided by R. And what is V? V is nothing but EMF divided by R. R is the resistance. EMF divided by R. Now see, EMF divided by resistance. Now see over here, we say, sir, this EMF, when it comes to the EMF, sir, we say it is nothing but, and this is R equivalent. This is R equivalent. Now, let's first find the R equivalent in this case. Sir, R equivalent is nothing but, when you have two resistors in parallel, their equivalent resistance is R1, R2. R1, R2 upon, then we have R1 plus R2. And what is R1? That is R. What is R2? That is R. That is R square divided by R1 plus R2 is 2R. This square and this will get cancelled. This is R divided by 2 over here. So equivalent resistance in this case is R by 2. So EMF in this case is BLV because this is EMF. So we say BLV divided by R equivalent is R by 2. You can say 2 BLV by R. This is the current in the circuit. Is this clear, guys? Is this clear? Let me know in the live chat if this is clear to each and every one over here. If this is clear to each and every one over here. Let me know in the live chat, my dear people, if this is clear to each and every one. Okay, great. Yes, both the resistance are in this case equal. This R1 is equal to R and this is also R. That's why I took R by 2. Now see, over here, you guys are supposed to tell me, find the EMF induced in the, find the EMF induced in the, not EMF, yes, find the EMF induced in the rod. Find the EMF induced in the rod. This is the rod we have over here. Okay. This is the rod we have actually over here. You guys are supposed to tell me the EMF induced in this rod. See, how do we find the EMF induced in the rod? Guys, When it comes to the EMF, we say, sir, EMF is nothing but we say it is simply BVL effective. It is simply BVL effective. It is simply BVL effective. EMF is simply BVL effective. Okay. Now, my dear people, when it comes to the EMF over here, we say, sir, magnetic field is B. And we say, sir, velocity is V. No, we don't know the magnetic field. Let's find the magnetic field. Sir, we say magnetic field at A distance because of the wire will be how much? You have to find the magnetic field over here. Wire is given. This is infinite wire. Okay, infinitely long. Because of this wire, magnetic field at A distance, we say magnetic field at A distance because of infinite wire. Magnetic field at A distance because of infinite wire. Sir, that is how much B is equal to mu naught I divided by 2 pi into R. R is A. This is the magnetic field because of this wire at A distance. Now, in that magnetic field, we have placed a rod. Okay, this is the magnetic field B. This is the magnetic field. And this magnetic field is being produced by the rod. In that magnetic field, we have placed this rod, which is moving with a velocity V and length is L. So EMF in this rod will be EMF is equal to BLV. B is mu naught into I divided by 2 pi A. This is B and velocity is V and length is L. BVL effective. BVL effective. So this will be the magnetic field in that case. Is that clear, guys? Is that clear? So over here, find the EMF in the rod. Over here, you guys are supposed to tell me EMF in the rod. And this rod is moving in the upward direction. This rod is actually moving in the upward direction. This rod is moving in the upward direction. How much is the EMF, guys? Let me know in the live chat. And make sure you like this particular session. Everybody of you like this particular session. All the people out there, guys, if you have not liked the session, like it as soon as possible. Now see, over here, see, we say, sir, this is the velocity, this is the velocity, okay, this is the velocity, and this is the length. Don't you think velocity and length here, velocity and length are parallel to each other, okay? So, EMF in this case will be 0. Why, sir? Because whenever any of the two, velocity, magnetic field or length, are parallel to each other, we say magnetic field in that case is 0. Can you tell me, this is important, this is very good. Find the magnetic field. Find the EMF in the rod, or you can also call it the square loop or the rod. This is at A distance. This distance, I'll write it over here. I'll write this. You have got a rod over here. Let me just make it something like this. This is the rod, okay? And this distance is actually from this point to this point. This is A, okay? The length of the rod is L. This length is actually L. This length is actually L. Okay, this length is actually L. You guys are supposed to tell me the EMF in this rod. You guys are supposed to tell me the EMF in this rod. This is the infinite wire over here in which current I is flowing. You guys are supposed to tell me the EMF in the rod. Find the EMF in the rod. Sir, when it comes to the EMF, you say, sir, when it comes to the EMF, we say it is nothing but BLV. Okay? And length I know, and it is moving with a velocity. It is moving with a velocity, we say, with a velocity V. BLV. Velocity I know, length I know. Now I have to find the magnetic field. See, when it comes to the magnetic field, listen to me very carefully. Sir, because of this infinite wire, at this point magnetic field is different. At this point magnetic field is different. Why? Because you are moving away from the wire, so magnetic field will decrease. So magnetic field through the entire rod is not constant over here. So magnetic field through the entire rod is not constant over here. Magnetic field through the entire rod is not constant over here. So you cannot directly say BVL. No, magnetic field is not constant. Now see, what we can do in this case, we say here, through the rod, we say magnetic field is not constant. Now what we can do in this particular case is, listen to me very carefully. Let me take a small strip. Let me take a small strip of width dx. Let me take a small strip of width dx, which is at x distance, okay, from the rod. This dx is at x distance from the rod. Okay. Now, sir, magnetic field at this x distance, which is dx width, from the rod will be how much? Listen to me very carefully. Sir, magnetic field at this point we know. We say magnetic field at x distance from the wire will be how much? Sir, we know magnetic field due to infinite wire is mu naught I divided by 2 pi into x. 2 pi r. Over here we are finding at x distance. Now we got the magnetic field at x distance and this will be constant. At a particular point it is constant. Now you tell me one thing. Sir, in this case, can you tell me the magnetic flux? Can you tell me the magnetic flux? Sorry, can you tell me the EMF induced this part? See, you know the magnetic field at over here. If you know the magnetic field here, you can find the EMF induced in this small element. Now, EMF induced in the small element. EMF induced in the small element. EMF induced in the small element will be how much? That is DE. Okay? Because total EMF is E and small EMF over here will be DE, because through the entire rod EMF will be E. In the small strip EMF will be how much? That is DE. Okay? And we know, sir, this DE will be simply BVL. Now magnetic field through this one at this point is how much? We know, sir, that is mu naught I divided by 2 pi into x. This is B. V is velocity. Rod is moving with a velocity V. This portion is also moving with a velocity V. BV. L, how much is the length of this rod? That is dx only. So we say this is dx. We say this is dx. Okay. This is the small EMF in this small element. In the entire rod, we say EMF is different. EMF will be, we'll find that EMF. You cannot say directly, I'll use the equation over here instead of B. What will you put instead of B? You cannot put the value of B over here. Why? Because the value of B, it is at this point. At this point, value of magnetic field would be different because it is. Just a second, guys. Dx. Okay, this one. Now in this case, to find total EMF, if we find the total EMF over here, what we can do is we say integrate. So if we integrate this one, that is integration of dE. Integration of dE is equal to, we say integration of, over here we have mu naught I divided by 2 pi x. We say mu naught I divided by 2 pi into x, divided by 2 pi into x. Then we have V dx. Okay. So EMF integration of dE will be exactly E, total E, that is EMF, is equal to, take mu naught out, take I out, divided by 2 pi V out, integration of 1 by x, then you have dx. Now the question is, sir, this x is variable. For this point x is this much, and for this point x is this much. Okay. Now we say if the length is L and this distance is A, can I say we have to integrate from A to A plus L? From A to A plus L, then the whole rod will be covered. So we'll have to integrate from A to A plus L, then the whole rod would be covered. So we say, sir, this EMF will be net will be mu naught I into V divided by 2 pi. And then you have integration of 1 by x is log of x. Okay. Integration of 1 by x is log of x. This is A plus L divided by A. And then you say, sir, this EMF is equal to mu naught I into V divided by, we say 2 pi. And then you say log of, in this x, first put the upper limit A plus L, then minus lower limit, we say minus log of A. Then after applying the log property, we say directly this one. This will be the final answer in this case. This was actually a good question, okay? Is this clear, guys? Is this clear? Is this clear to each and everyone? Is this clear to each and everyone? Okay. Okay. Let's finish this topic first, okay? We'll give break. Wait for some time, I know. Listen to me very carefully. Let's finish this topic over here. That is, we say induced electric field. What does induced electric field actually mean? What does induced electric field actually mean? Let me just tell you, when it comes to the induced electric field, let's suppose we have got We have got a loop over here or a ring over here, circular ring over here. And I'll place a magnet over here. This is the magnet I have actually over here. Okay. Yes, sir. This is the magnet. Okay. And my dear people, this magnet, if I move it towards this one, if I move it towards this ring, if I move it towards this coil with a velocity v, we say magnetic field through the coil will change. On moving the magnet towards the coil, we say magnetic field through the coil will change. Okay. So we say, sir, this magnet is moving towards the coil. So we say flux through the coil is changing. Okay. If you take it away from the coil, less field lines will cross the coil and flux through the coil will decrease. This is what I told you before also. So we say flux through the coil will change. So when flux through the coil changes, we say current starts flowing through the coil. Through the coil. We say current starts flowing through the coil. Okay. Now, my dear people, listen to me very carefully. When this current flows through the coil, we say, sir, it means charge is flowing. We say, sir, charge is flowing. Charge is flowing through the coil. Through the coil. Okay. Charge is flowing in the coil. In the coil. Charge is flowing in the coil. In the coil. Charge is flowing in the coil. Listen to me very carefully. Sir, when magnetic field is basically brought close to the coil, more field lines are crossing through the coil. More field is crossing the coil. We say because of that, current starts flowing in the coil. Let's suppose this is the current which is flowing, something like this. We say, sir, when current flows through the coil, it means charge is flowing. Charge is flowing because current is the flow of charge. It means, sir, charge is flowing. Current is the flow of charge. Current is flowing means charge is flowing. Sir, we know charge only flows when there is electric field. So as listen to me, as charge flows because of electric field. Sir, charge flows because of electric field. We have studied if you have this electric field over here, if you place a charge in this one, sir, we say force acts on this charge and it starts moving. So we say charge flows because of the electric field. We say, sir, we say over here means electric field is also present. Electric field is also present. Okay, sir, on changing the magnetic field, we say current is being produced. Sir, current is being produced means charge is flowing. Sir, charge flows because of electric field. So this is the direction of electric field. This is the direction of electric field in this case. Okay. This is the direction of electric field. Now, my dear people, listen to me very carefully over here. I'll tell you a golden and important point. Sir, this electric field looks like over here. It is of the cyclic electric field, or this electric field is what we call the induced electric field. And this electric field is being produced by changing the magnetic field or flux. So by changing the magnetic flux, induced electric field is produced. So if you change the magnetic flux through the coil, we say, sir, electric field is being produced. If you change the flux, current is being produced. Current is being produced means charge is flowing. Charge is flowing means electric field is being produced. See, if flux changes through the coil, we say current is produced. Sir, if current is produced means charge is flowing. If charge is flowing means electric field is there. So on changing the flux, we say, sir, electric field is being produced. By changing the flux, electric field is being produced. And that electric field is what we call the induced electric field. That electric field is what we call the induced electric field. And if I just tell you the value of that electric field, listen to me very carefully. We say this electric field, we write it something like this, E dot dl. Closed line integral E dot dl. Sir, this is of the circular shape, circular form or cyclic shape. That's why we write closed line integral E dot dl is equal to, we say, sir, d phi divided by dt is equal to d phi divided by dt. This is what we call the induced electric field. This is what we call the induced electric field. Okay? This is what we call the induced electric field. This is what we call the induced electric field. This is what we call the induced electric field. Okay? This is what we call the induced electric field. This is what we call the induced electric field. So, induced electric field, how do we write the induced electric field? E is integral E dot dl, integral E dot dl, integral E dot dl. Just a second, guys. Integral E dot dl is equal to minus d phi is equal to d phi by dt. Okay? Or you can write it something like this also. Further, that is equal to EMF. So EMF is equal to d phi by dt. EMF is equal to d phi by dt. This EMF is equal to d phi by dt. Now, my dear people, over here, listen to me. If I just ask you one single question, Now see, if I ask you one single question over here, see, induced electric field inside the region of magnetic field. Everybody listen to me very carefully. Induced electric field inside the region of magnetic field. Let's suppose you have got the magnetic field over here. You have got the magnetic field over here. In this region, magnetic field is present. In this region, magnetic field is present. In what region? I'll show you something like this. This is the region in which magnetic field is present. Okay? Yes, sir. This is the region in which magnetic field is present. This region. This is not a circular loop. Don't consider this as a loop. This is the region in which magnetic field is present. Okay? Yes. Now, and if this magnetic field is changing, B is changing. Sir, we know, sir, on changing the magnetic field, electric field is being produced. And if I say over here, my dear people, if I say over here, let's suppose this is capital R. This is capital R. So magnetic field is present in the capital R region. And I want to ask you the electric field, value of electric field at small r distance. At small r distance. Okay. So this much is the magnetic field is present in the capital R region. You have to tell me the electric field inside the magnetic field. This point is inside. And if I talk about this point, this is outside. This point is inside, this point is outside. You have to tell me the magnetic field inside. Electric field inside. That's what we call induced electric field inside the region of magnetic field. So we say this inside, I'll make it over here. This inside, I'll make it over here. It would be something like this. Inside the region of magnetic field. Okay. So magnetic field is present in the capital R region and you have to find the electric field at small r distance. I hope you are getting me what I'm trying to say in this case. And we say, my dear people, listen to me very carefully. Directly, I'll write the expression. We say here, 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 magnetic field is present in, we say, capital R region, and have to we have to find and we have to find we say we have to find electric field. We have to find electric field at small r distance, that is inside the magnetic field, that is inside the magnetic field. Okay, now see, if we write this, sir, this electric field at this small r distance inside the magnetic field will be simply, we say r divided by 2, and then we say dB divided by dt. So what is r? R is the distance at which you have to find the magnetic field. What is this dB by dt? dB by dt is nothing but change in magnetic field. Okay, how much is the change in magnetic field in this case? dB by dt is the change in magnetic field. Okay, this is basically the magnetic field inside the region of electric field. So this is the electric field inside the region of magnetic field. Now, next one I have over here, induced electric field outside the region of varying magnetic field. Let's suppose you have this magnetic field over here. You have this magnetic field over here. You have this magnetic field over here. And this magnetic field is present in which region? Let me just make it over here. This magnetic field is present, let's suppose, in this region. Okay, in this region. It is present in this region. Let me make it something like this. Magnetic field is present in this region. Okay, now you are supposed to tell me, we say, sir, magnetic field is present in the capital R region, and in this case you guys are supposed to tell me electric field outside the region of magnetic field. Electric field outside the region of magnetic field, and I'll make it something like this. I'll make it something like this. Okay, electric field outside the region of magnetic field. This point is outside. Okay, so this point, this circular loop, this is the circular loop over here. This is the circular loop or circular loop. And this one is not the circular loop. This is the region of magnetic field. Region of magnetic field is where magnetic field is actually present. And in this case, this one is the region of magnetic field and this is the circular loop. Okay. And same is the case over here. In this case, you guys are supposed to tell me the magnetic field, electric field at this r distance. And in this case, we say r is greater than r. And over here, we say r is less than capital R. So what is the value of magnetic field in this particular electric field? We say electric field at this r distance will be, sir, this is nothing but, we say simply, that is r square divided by 2r. Then we have dB divided by dt. What is R? R is the region in which magnetic field is present. What is small r? Small r is the region at which we have to find. Small r is the basically the point where we have to find the electric field. So we say this is the electric field at small r distance outside the region of changing magnetic field. Is that clear, my dear people? I just need to know in the live chat if this is clear. If this is clear to each and every one, let me know, guys. Let me know if this is clear to each and every one. Let me know in the live chat if this is clear to each and every one, guys. If this is sorted. Is this clear, guys? Everyone, all of you. Everyone means everyone. I want all of you to basically give me signal in the live chat with the fire emojis so that I can move forward. So that I can move forward. Got you. It's okay. बराबर वन जन्य बुद्धिमत्ता ब्रेक नेक्स्ट में नो टॉपिक स्टार्ट करो ओके ओके बोला 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 अच्छा okay guys, let's take a break. Okay, we'll be back at break till we have 9:50. 9:50 break till 9:50. Okay, guys, have the dinner. Okay, I'll also get done with the dinner. Okay, guys, let's start the session. All right, people, welcome back to the session. Let's start with this particular topic. That's what we call the self-induction. Let's start with the self-induction. Okay. I hope everyone is back. Now see, what is self-induction all about? What is self-induction all about? Okay. See, let's suppose I take a coil over here. Okay. This is the coil which I take over here. Okay. This is a coil of N turns, or you can call this as a solenoid also. You can call this as a solenoid also. Coil of N turns or a solenoid. Okay. And in this coil, we say, sir, current I is flowing. If I say I current is flowing in this particular coil. We know, sir, whenever current is flowing in the coil, because of this current, magnetic field will be produced in this coil. We know whenever current flows through a coil, magnetic field is produced. So we say due to the current, we say magnetic field is produced inside the magnetic field is produced inside the coil. Magnetic field is produced inside the coil. So due to the current, we say magnetic field is produced inside the coil. Okay? Yes, sir. Now listen to me very, very, very carefully. Sir, if magnetic field is produced inside the coil, we say that magnetic field would be something like this. That magnetic field would be something like this. Now, clearly you can see this is a coil something like this, and magnetic field is crossing the area of the coil. We say flux is being produced over here. So, flux is being produced here. So, we say flux is being produced here. Okay? Yes. Now, we say, sir, if more you send the current inside the coil, more magnetic field will be produced. So we say more is the current in that case. More is the current in that case. Okay, sorry, more is the flux in that case. So more you are increasing the current, we say magnetic field will increase. And on increasing the magnetic field, we say, sir, magnetic flux through the coil will increase. So I can simply write this magnetic flux is directly proportional to the current. More is the current, more is the magnetic field, and more is the flux through the coil. So magnetic flux is directly proportional to the current. And replace this constant, replace this proportionality with a constant. We say, sir, phi is equal to L into I. Where this L is the constant of proportionality. Where L is the constant of proportionality. Okay? Where L is the constant of proportionality. Okay? And this L is called, we say, self-inductance. Okay? This L is what we call the self-inductance. Okay. And we say the value of this L, is nothing but we say mu naught, then we say N square A into L. Sir, what is mu naught? Is mu naught permeability of free space. And what is N? N means, sir, number of turns. Number of turns in the coil. A means, sir, area. Okay, area of cross section. Area of cross section. Cross section. And when it comes to L, L means length. L means length of this particular coil, length of the solenoid over here. Okay, so we say this flux is equal to, that is L into I, where L is what we call the self-inductance. Okay, where L is what we call the self-inductance. Now listen to me very carefully. I'll just write a point over here. If I say if current in the coil, is changing, if current in the coil is changing, or if current in the coil is increasing, we say, sir, due to this changing current, if you are sending the increasing current, due to this increasing current, magnetic field would be increasing. We say, sir, magnetic field is increasing. Okay. We say, sir, if magnetic field is increasing, we say due to which we say flux is increasing. We say flux is increasing. We say flux is increasing. Okay. Yes. If current in the coil is changing, we say magnetic field is changing. We say flux in the coil is increasing or changing. Okay. Now, my dear people, if, sir, flux is changing, don't write increasing, we'll write the word changing over here. It can be decreasing, increasing. We say, sir, changing. Changing. Okay. Now, if I say, sir, flux, if I say current in the coil is changing, sir, due to that current, we say flux in the coil is changing. Sir, how do I write? We know, sir, flux is equal to L into I. Now, if the current is changing, how do I write the change in current? We say, sir, di divided by dt. This is what we call the change in current. And L is constant, keep it as it is. By changing the current, we say, sir, flux also changes. That is d phi divided by dt. Okay. Yes, sir. Now, my dear people, over here, we say over here, as we know from Faraday's law. From Faraday's law, we say, sir, EMF is equal to, we say, sir, minus d phi divided by dt. EMF is equal to d phi divided by dt. Now, instead of this d phi by dt, can I just write this? So we say, sir, this EMF is equal to, I would say, minus L di divided by dt. EMF is equal to minus L di by dt. So we say if current through the coil is changing, we say flux through the coil is changing. And if flux through the coil is changing, we say, sir, EMF is being produced. And that EMF is what we call the L di by dt. And this process and this process of reducing the EMF is called self-induction. What does self-induction mean? Self-induction is nothing but EMF is being produced inside the coil. Okay, so that EMF is equal to minus L di by dt, and this is what we call the self-induction. What I said is that I have got a coil over here, and in this coil current I is flowing. Because of this current, magnetic field is being produced. Okay, because of this current, magnetic field is being produced. Sir, magnetic field crosses the area, so flux is being produced. So we say flux is proportional to the current. Sir, on replacing this proportionality, we put a constant, that is L, where L is called constant of proportionality and is called the self-inductance. Okay. And we say over here, phi is equal to L into I. Now, if I say, sir, this current is changing, so I can write the changing current something like this, di by dt. On changing the current, we say, sir, flux will also change. We can write it something like this. And this, we know from the Faraday's law, sir, if flux through the coil is changing, we say EMF is being produced. So I can write EMF is equal, instead of this, I'll write L di by dt. So this process of producing the EMF in a coil is called the self-induction. Is this clear, my dear friends? Is this clear, my dear friends? Is this clear, my dear friends? Now, I say over here, let me just tell you one thing. Let's suppose I say I have a coil over here. And in this coil, you are sending the current which is increasing. This current which you are sending inside the coil is increasing. Okay? Current is increasing. Now, sir, inside this coil, we know when we send the changing current, we say, sir, magnetic field will be changing. We say, sir, current, flux will be changing. And by changing the flux, we say, sir, EMF is produced. And that EMF is minus L di divided by dt. Okay? So we say due to changing current, sir, we say due to changing current, or let's call this as primary current. Due to primary changing current, and which is primary. Okay? Due to this changing current, changing magnetic field is produced, and that changing magnetic field crosses the area. So changing flux is being produced. Flux also changes. So which produce the EMF, that is equal to L di by dt. Now, sir, due to the changing current or primary current, we say EMF is produced. EMF is produced. And this is called the self-induction. Now, if EMF is produced inside the coil, we know, sir, from Ohm's law, sir, if there is EMF or potential difference, we say V is directly proportional to I. If there is potential difference, there is current. If there is potential difference or EMF, there is current. Okay. If you increase potential difference, current will increase. Now, if EMF is present in this inductor, in this, we say coil, over here, we say current is also induced. We say current is also induced. So we say current is also induced. Or we say induced current is being produced. Let me write it something like this. Induced current. Don't write induced. Let me write secondary current. Secondary current is being produced due to that EMF. Okay. So we say, sir, because of the primary current, EMF is being produced. Because of this EMF, secondary current is being induced. And I can show that secondary current something like this. This is what we call I induced. Sir, why did you show the direction of the induced current opposite to the primary current? Because, sir, primary current is increasing. Lenz's law says that if primary current is increasing, induced current will be in such a way so that it opposes the increasing current and it supports the decreasing current. So means if you are sending the increasing current, so this will create an induced current which will oppose it. So you can show this like a battery. It would behave like a battery. Let's suppose this is a battery. This is a primary current in the battery. So we can show it something like this. This will be the positive terminal and this will be the I induced. This will be the I induced in this case. Now, if I tell you the another case over here, let's suppose I show you something like this. Let's suppose I show you something like this. Let's suppose I have an inductor over here. And in this inductor, the current is decreasing. In this one, current is decreasing. Now, my dear people, listen to me very carefully. Listen to me very carefully. If the current in this inductor is decreasing, if the current in this inductor is decreasing, listen to me very, very, very carefully. We say, sir, EMF is being produced over here. Sir, EMF is equal to minus L di by dt. Sir, because of this EMF, another current is being induced in this one. And I show the direction of that induced current in this direction. Why? Because this current is decreasing. So this induced current will support the decreasing current, because Lenz's law says that you have to support the decreasing current and you have to oppose the increasing current. Guys, tell me, is this crystalline clear? Is this crystalline clear? And if you have to show the battery like over here, so we say it would be something like this. So current will leave from positive terminal. Is this crystalline clear? Let me know in the live chat, guys. You have a question over here. The current passing through a choke coil of 5 Henry is decreasing at a rate of 2 ampere per second. The EMF developed across the coil is. Sir, when it comes to the EMF, we say EMF is simply minus L di divided by dt. So we say, sir, in this case, EMF is equal to minus L. L means the inductance. Over here, it is given 5 Henry. So it will be simply 5. Okay. And then di by dt. See, current is decreasing at a rate of 2 ampere per second. Means di by dt is nothing but minus 2, because current is decreasing. So this is a rate of change of current. Current is decreasing at 2 ampere per second. That is minus 2. So we say minus 2. 5 into 2 is, we say, sir, plus 10 volts. EMF will be plus 10 volts. Option A. Option A. Simply consider this an inductor. That's it. Or the solenoid. Di by dt is minus 2. L is 5. So this will be 10 volts. Now, my dear people, listen to me very carefully over here. Listen to me very carefully over here. We have a question. I have shown you the questions of this type in the current electricity also. The question is, you have got point A, then you have a resistor, you have a battery, and you have an inductor. Now see, listen to me very carefully. We have to find, in this case, VB minus VA. We have to find VB minus VA. In this case, you guys are supposed to tell me VB minus VA over here. VB minus VA over here. Okay? VB minus VA over here. Now see. What we do in order to solve this type of question, let's suppose the potential at this point is VA and potential at this point is VB. We have to find potential VA minus VB. VA minus VB. How do we find it? First and the foremost thing is, let's first make this point over here. That is, let's write the potential VA. Yes, sir. Now you have this resistor over here. Sir, when it comes to the resistor, we say potential difference in case of resistor V is equal to I into R. Now V is equal to, what is the current in the resistor? Now the network shown in a figure, a part of this, it is the current is 4 ampere. We say this current, just a second. We say this current is nothing but 4 ampere. This current is nothing but 4 ampere. So we say V is equal to I into R. That is 4 into resistance of this one is how much? That is 1. 4 into 1. So V is equal to 4 volts. And the direction of current is this. So this will be higher potential. This will be lower potential. I have told you current flows from higher potential to lower potential. That's why this is positive, higher, negative is lower. Now, my dear people, over here, if you have to replace this resistor with a battery, you can replace it something like this. Make a battery over here. And my dear people, what is the potential difference or EMF of the battery? That is 4 volts. How did you get it? I into R. That is 4 volts. And then you have over here, then make the next battery as it is. This is 12 volts. Okay, 4 volts, and then you have 12 volts. And then, sir, this is the inductor over here. When it comes to the inductor, sir, how do we find the EMF in case of inductor? This is the formula by which we can find the EMF in case of inductor. So let me write it over here. This EMF is equal to minus L di divided by dt. Sir, this EMF is equal to minus, this EMF is equal to minus, and when it comes to L is how much? We say, sir, 5 millihenry. So that is, we say, sir, 5 into 10 raised power minus 3. It's millihenry. Okay. And then di by dt, the current is increasing at a rate of 10 ampere per second. So means di by dt is given as 10 raised power 3 ampere per second. Okay. So we say this and this will cancel. So EMF in this case is given. EMF in this case will come out to be, that is, we say simply over here is, that I say over here, that is 5 volts. Okay. I say over here 5 volts. Is that clear, my dear people? Is that clear, my dear people? Okay. Is that clear, guys? Okay. So now, sir, battery, you made it over here as it is, and then you make this inductor over here. So we say this will be simply, that is nothing but, what is this? That is 5 volts. And this is the point B over here. This is the point B over here. That is potential VB. See, if you have to find potential difference VA minus VB or VB minus VA, what you are supposed to do is, first convert this entire setup, convert this entire branch replace it with the batteries. Instead of this resistor, make the battery over here. So what is the potential difference? V is equal to IR, that is 4 volts over here. Instead of this also, you make the battery over here. How to find EMF? Minus L di by dt, or write mod of EMF is equal to L di by dt, that is 5 volts. Okay. So this is basically how do we exactly do it. Now move from A to B or from B to A in this particular case. So when we say, sir, select the path, this also I have told you. Now select the path. So if you select the path from A to B, so first you write VA, then minus this 4 volts, then minus this 12 volts, because in case of a battery, if we move from higher potential to lower potential, we write minus 4. Over here also minus 12. And this also we say, sir, minus 5 volt is equal to VB. Okay. Now, if you find VB minus VA, that is equal to minus 21 volts. Minus 21 volts. Is that clear? Is that clear, guys? Let me know in the live chat with the fire emojis. Is this clear? I'll show you one more question on the same pattern. Now see over here, you have to replace this with the batteries. First and the foremost thing is find the potential difference in case of the resistance. Sir, this is, we say plus and minus because current flows from higher to lower. So we say V is equal to I into R. So V is equal to, current is how much? That is 4. And R is 2. So we say, sir, 8 volts. Okay. Now I can make it something like this. This is the point A. Okay. And over here, I'll make a battery something like this. And how much is the potential difference of this EMF of this battery? That is 8 volts. And you have got over here, that is 5 volt battery. Instead of this also, you make the battery. How do we make the battery over here? Listen to me very carefully. We say, sir, EMF in case of resistor In case of inductor, EMF is equal to minus L. We have di divided by dt. And then you can write this EMF is equal to minus L. L is how much? That is 10. Di by dt is how much? In this case, the and is increasing at a rate of C. You read the question. The network shown in the figure is a part of a complete circuit. If at certain instant the current is 4 ampere and is increasing at a rate of 10 ampere per second. So over here, the current, this is increasing at a rate of 10 ampere per second. Okay. So we say this EMF will come out to be 10 into 10 is basically 100 volts. Okay. This is mod of E. So 100 volts will be, so make a battery over here. That will be something like this. And this will be simply, we say 100 volts. And this is the point B over here. Is that clear, my dear people? Let me know in the live chat. And if you find the value of VB minus VA, VA minus VB, move from A to B. Select the path from A to B. So first convert this in batteries, then move from A to B. Select the path from A to B. So if you select the path from A to B, first we write the potential of this point, then potential difference of this one, that is 8 volt. Now we take this as negative. Why? Because we are moving from higher potential to lower potential. Here also we are moving from higher potential to lower potential. Here also we are moving from higher potential to lower potential is equal to, we say, VB. So VA minus VB will be simply, VA minus VB will be simply 113 volts. Next question. This was the question which was asked in NEET 2016. Can you tell me the answer of this particular question over here? A long solenoid of 1000 turns. When a current 4 ampere flows through it, the magnetic flux linked with each turn of the solenoid is this. The self-inductance. When it comes to the self-inductance, we say phi is equal to L into I. Okay. So in this particular case, we are given a solenoid. We are given, this is a solenoid, okay? And the number of turns in the solenoid is 1000. And flux through one turn is given as, 4 into 10 raised power minus 3. So flux through one turn is given as 4 into 10 raised power minus 3. Flux through n turns or 1000 turns will be how much? So we say, sir, flux through 1000 turns is how much? That is, we say 1000 into 4 into 10 raised power minus 3. Then we have is equal to L into I. L is L. Okay. And when it comes to the I is basically 4 ampere over here. 4 and 4 will get cancelled. 1000 and this will get cancelled out over here. L will come out to be 100. We were supposed to calculate L. We were supposed to calculate this L. Okay. Let's move on to the next question. This is a good question actually, and this I'll give you as homework. I have already shown you two questions on the same pattern. Let me just show you here only. See, you have a battery over here. You have capacitor. Sir, when it comes to the capacitor, we say Q is equal to CV. So V is equal to Q divided by C. How much is the charge on capacitor? That is 2. This is 10. Capacitance is 10. That is 1 by 5. 1 by 5 volts. Now in case of inductor, we say EMF is equal to minus L di by dt. L di divided by dt. And in this particular case, I will tell you the rate of change of current. That is 0.5 ampere per second. This is given as di by dt is given as 0.5 ampere per second. That is minus 0.5 ampere per second. Okay. Now, find the EMF in this case, and in case of resistor also you use V is equal to I into R. So once you get the potential difference in resistor, you get potential difference here, you get potential difference here. And then redraw the circuit, make the batteries, and then find the potential VA. You guys are supposed to tell me find VA. Okay. This is the homework. This is an easy question. I have already shown you the concept. This is the homework. Let's move on to the next one. Yes, this one. That is magnetic energy. Magnetic energy is stored in a solenoid, or magnetic energy density. Magnetic energy density. Listen to me very carefully. If I tell you in this particular case, let's suppose we have a capacitor over here. We say capacitance is C, potential difference is V. This is a capacitor. So we say its capacitance is C, potential difference is V. So if I ask you, sir, how much is the energy stored in the capacitor? Sir, we stored charge over here. How much is the energy stored in a capacitor? You say, sir, energy stored in case of capacitor is 1/2 CV square. This we have studied before. But when it comes to an inductor, when it comes to a solenoid, let's suppose you have got a solenoid over here, okay? And in the solenoid, current I is flowing. I is the current which is flowing in the solenoid. How much is the energy stored over here? Energy stored. We say in this case, energy stored will be simply 1/2. Sir, this inductor or this solenoid has inductance, self-inductance, that is L. Like this capacitor has capacitance C. Current in this case is I. So we say 1/2, then we have L I square. Like over here we have CV square, we have Li square. This is the energy stored in a solenoid. This is the energy stored in a solenoid. Now, as we know, sir, when it comes to this, L is equal to mu naught N square A into L. I just told you, sir, solenoid, this self-inductance is equal to mu naught N square A into L. If you put the value over here, you'll say, sir, this energy will come out to be, that is 1/2. Instead of this L, you can say mu naught N square A into L. Then you have this I square over here. Yes. What I want you guys to do is that divide this A into L over here. You say, sir, E divided by AL is equal to, we say 1/2 mu naught N square into I square. What is this? This is what we call the energy density. This is what we call the energy density. Sir, what is energy density? Energy density is nothing but energy density is energy stored per unit volume. Let's suppose you have this inductor, okay? Area of cross section is A and this length is, let's suppose, L. So it will have some volume, area multiplied by length. So if energy stored in the entire inductor is E, if I ask you to tell me energy stored in the unit volume, you say E divided by A into L, energy per unit volume. Volume is over here, A into L. So energy per unit volume is how much? That is 1/2 mu naught N square into I square. This is also called the energy density. Is this clear? This is the total energy stored, total energy stored. And this is the energy per unit volume. Is that clear, my dear people? Is that clear? Now we have over here the growth of current. Is this clear, guys? Let me know in the live chat. And if you have not liked the session, like it as soon as possible, because that is mandatory. Okay, let's talk about the growth of current. Now see, what does growth of current actually mean? Let's suppose you have an inductor over here, okay? And you have a resistor over here. And you have this switch and you have a battery. You have a battery over here, okay? This battery has EMF E, okay? And potential difference across this inductor is VL. And potential difference across this resistor is, we say, VR. That is VR. This is VL and this is VR. This is VL and this is VR. Okay? Listen to me very carefully, my dear people. Sir, we have this potential difference across the inductor and potential difference across the resistor. And you have this E. Now, what I want you guys to imagine in this case is that you close this switch, means you switch on this particular circuit. When you close this switch, I'll just write over here initially, when switch is just closed, okay, or we are about to close the switch, this is that but time, okay, or we say at time t is equal to 0. When switch is just closed, when we just close the switch, we say at that particular point of time current is 0. No current has exactly flown. We have someone in the house.
What's up, people? How are you doing? How are you doing?
Yeah.
What's up, guys? I'm seeing you after so long. Yes. How are you all? How are you all?
Fire emojis in the live chat.
Why the Josh is down, people? I fail to understand why the Josh is down. Yeah. Where is the Josh of the day one? Where is the Josh of the day one?
That Josh is gone now. Everybody
Is that
down, huh?
I want everyone to be active in the chats, yeah? So I would want some fire emojis in the chats, people. Quickly in the chats. I would want some fire emojis. Yes. That's what. Yes, I would want some fire emojis in the chats. Perfect. So I hope, first of all, salute to you guys salute to all those students basically who have been sincerely following this particular series which we have been running on YouTube. I think it is day 36 today or 37, something like that, right? So till now we are done with 37 chapters. So basically, we are done with half of the syllabus. So all those students who do not have any sort of backlog here, salute to you, because it's not really very easy to follow all the marathons, that to every day, that to for like 5, 6, 7, 8, 9, 10 hours like that. Yeah, that's wonderful. That's great. And do you know, you guys must be knowing I was not well, so it's almost been a week. I've not taken any session, right? I'm still in the recovery mode, but on 20th of this particular month, right, 20th Jan, we are doing the chapter electrochemistry. I hope you know that. Yeah? I hope you know that.
And make sure you like that session, otherwise he'll cancel the session.
They've already liked it. All right, people. So you guys carry on. So I thought to just interrupt you guys so that your energy might be a bit increased. Yeah. Thank you so much. I'm getting better. Perfect, guys. Chalo, you carry on. See you on 20th. Yeah. Chalo.
Okay. So guys, we have covered half of the NEET syllabus, means approximately we have crossed the 380, 370 marks, okay, when it comes to the NEET. Now see. Now see. So what I'm just trying to say in this particular case is that when switch is just closed, means at time t is equal to 0, current is 0. Okay. We have just closed the switch. At t is equal to 0, we say I is equal to 0, current is equal to 0. Okay. Now, current will start growing after some time. We know that. Let me just tell you, let's suppose if I just tell you over here, we have this resistor in this case, and we have got a battery over here. Okay. Now, if there is switch, if we have closed the switch, we say if this is 20 volts and this is 10 ohm resistor, sir, how much is the current? We say current is V by R, that is 20 divided by 10, that is 2 ampere. So current will reach immediately from 0 to 2 ampere, okay, in this particular case. But listen to me over here. We say when switch is just closed, current at that time is 0. Now current will grow, current will become maximum. Current will become maximum over here, but not instantly, not instantly. Why? Because inductor is being used over here. Inductor is present. Because, see, when you close the switch, current wants to become maximum, but inductor is present. Sir, if current wants to increase, wants to become maximum, sir, inductor opposes the change. Inductor opposes the increasing current and supports the decreasing current. This coil, it opposes the increasing current. So this will not let that happen, that current should grow and reach maximum instantly. Okay, so we say at t is equal to 0, current is equal to 0. Okay, now we say now current wants, we say current, now we say current wants to become maximum. Current wants to become maximum immediately or instantly. Current wants to become maximum instantly. Current wants to become maximum instantly, but inductor opposes. This means this is inductor opposes the change, Inductor opposes the change. Okay. So we say, sir, at t is equal to 0, current is 0. Now current wants to be maximum, like over here in this circuit. In this circuit, I have shown you over here, only resistor is present. So when you close the switch, current reached 2 ampere, instantly it became maximum. But over here, it will not reach the maximum value instantly. Let's suppose current has to reach 10 ampere. It will not reach 10 ampere instantly, but it will go up, but slowly. So we say over here, listen to me very carefully. So we say in this case, growth of current will take place. We say growth of current will take place. So here, growth of current takes place. Okay, current will not reach the maximum value instantly, but it will grow, and after some time, we say at t is equal to infinity, after a very long time, we say current becomes maximum, I is equal to I maximum, current becomes maximum. Okay, so if there was no inductor present in the circuit, we say in that case, current will reach the maximum value instantly. Current will reach the maximum value instantly. Okay, I hope you got it. Now see, you tell me one thing. If I say, sir, can you tell me the value of this VL over here? You say, sir, the value of VL initially, listen to me very carefully. We say at time t is equal to 0, I is equal to 0. Can you tell me, sir, what is the value of VL and what is the value of VR? We say when it comes to, sir, VR, it is equal to I into R. Current into resistance. We say initially current is 0. So you can say VR is equal to I. I is how much? I in this case is 0 into R. So that will be 0. So initially at t is equal to 0, we say potential difference across resistor is 0. Why? Because there is no current. Because at t is equal to 0, current is 0. Now, if I say, my dear people over here, if I say, what is the value of VL? We say, sir, VL is, that is potential difference across inductor. How do we find it? L di by dt. We say, sir, L di divided by dt. See, current initially is 0, but di by dt means rate of change of current. Di divided by dt is not equal to 0 initially. Di by dt is not equal to 0, but I is 0. Current, see, current initially is 0, but it wants to change. It wants to reach the maximum value. It wants to reach the maximum value. So we say di by dt is not equal to 0 in that case. So we say di by dt is maximum and is maximum initially. Initially it wants to change, but due to the inductor it is opposing. So that's why we say it is maximum. So VL is equal to maximum in that case. And we can say initially, sir, this potential difference of the battery is being divided into VL plus we say, sir, VR. And VR is initially 0. So we say E is equal to VL. This is initially. I hope you got it till now. Okay. We haven't finished the story yet. Sir, what does growth of current mean? Growth of current means if you have inductor, resistor, battery. This is a circuit. If you close the switch, sir, current wants to reach the maximum value now because you close the switch, it will send the current and will reach the maximum value, 10 ampere, 20 ampere. But sir, inductor is present over here. So inductor will not let that happen. So current will reach the maximum value, but after some time, it will grow. So we say growth of current will take place. And initially we say VR is 0 and VL is maximum. Now we say at t is equal to infinity, we say current I is equal to I max. Okay. And when current has reached the maximum value means current is now constant. Current is now has become the constant. Okay. So this current which is present over here, this has become the constant. Initially it was 0. It has become the maximum and constant. Now, my dear people, we say over here, V is equal to I into R. Let's talk about the potential difference across a resistor. This is potential difference across a resistor. Yeah. Now, if we talk about the potential difference across the resistor, we say, sir, current in this case is maximum. So this we can write over here. If this is maximum, this is the resistance over here. So we say this VR will be in this case maximum because current in this case is maximum. Now, if I just talk about, sir, VL, that is potential difference across inductor. That is L di divided by dt over here. Now, di by dt, sir, finally, when current has reached the maximum value, the current wanted to grow 0, 1, 2, 3. If I say 10 is the maximum, it has reached maximum. It cannot go 11. Why? Because 10 is the maximum. Yeah. Because 10 is the maximum. So we say finally, when current is maximum and is constant, we say a rate of change of current is 0. Current will not change now. So we say di by dt is equal to 0. So we say VL is equal to 0. So at time t is equal to 0, we say VR is 0 and VL is maximum. At time t is equal to infinity, we say VR is maximum and VL is 0. These are the two important points which you need to understand in order to solve the problems, in order to solve the questions. That's why this is important. Now, my dear people, listen to me very carefully over here. Listen to me very carefully over here. See, at time t is equal to 0, current is 0. At time t is equal to infinity, current is maximum. If I say in between the two, if I say in between, current has grown and reached maximum value. Current has grown and reached maximum value. So we say at t is equal to t. We say at t is equal to t. T is the time in between. And t is equal to infinity is equal to the final state or steady state. Okay, that is initial state. This one is steady state. At t is equal to t. See, let's suppose the current has to grow from 0 to maximum. Okay, we say over here it is 0, over here it is maximum 10 ampere, 15 ampere, whatever it may be. So in between the two, let's suppose time t is equal to t is the time when it is in between, when it is in growing phase. What is the value of current? Now, you need to understand this one. What is the value of current at t is equal to, at t is equal to t? At t is equal to t. Now we say at t is equal to t, in between, the value of current I is equal to I naught. What is I naught? I naught is the maximum current or the peak current. I naught, or you say this as I naught, peak current. We say 1 minus e raised power minus RT divided by L. E raised power minus RT divided by L. There is a long derivation for this, but I am showing you directly to the point over here. This is the current when the current was growing. This is the current at time t is equal to t. I naught 1 minus e raised power minus RT by L. What is I naught? I naught is basically maximum current or peak current. Peak current. And when it comes to R is resistance. R is resistance of resistor. And we say T is time, L is inductance. Okay, L is inductance of the inductor, because you have resistor, you have inductor. So this is we call the current. So that's what I was trying to make you understand. What does growth of current mean? Growth of current means if the current is growing, reaching maximum value but takes time. And if current reaches maximum value instantly, in that case we say, sir, there is no growth. It reached the maximum value instantly. Okay. So we say, my dear people, in this case, so this is the value of current. I is equal to I naught 1 minus RT by L. Now there is one thing, that is what we call the time constant. Time constant. This time constant is equal to tau, and this is equal to R by L. This is equal to R by L. This is equal to R by L. Okay. Now, my dear people, if I just say, what is this time constant? This time constant is equal to tau, it is equal to R by L. If you divide resistance with inductance, you will get the time constant. Whatever is the value of resistance, whatever is the value of inductance, divide it, you will get the time constant. Now, can I just write, if I do it something like this, 1 upon tau will be L divided by R? Yes, sir. Do the reciprocal. Now, my dear people over here, you guys tell me one thing. You guys tell me one thing. This is L by R, sorry. This is L by R. This is L divided by R. And if you do the reciprocal, this will be R by L. This will be simply R by L. Now, I want you guys to put this in equation first. I want you to put this in equation first. This is the equation first. I want you to put this in equation first. Instead of this R by L, what we can write over here? See, instead of R by L, we can write 1 by tau. So we say I is equal to I naught 1 minus e raised power minus RT divided by L. So we say I is equal to I naught. We say 1 minus e raised power minus R by L. Instead of R by L, we write 1 by tau. So that will be T by tau. Okay, that will be T by tau. Now, if I say, let's suppose, we say if T is equal to tau. If I say time, the value of time is tau. What does that mean? See, first of all, we define the time constant. Time constant means L by R. So, means if you put the value of inductance over here, divide it with resistance, you'll get tau. Okay. Now, if I say the value of time is equal to the value of tau, value of time constant. So let's see how much will be the current. If t is equal to tau, then find current. Then find current at that time. At that time. Let's see. Sir, we can write over here I is equal to, we say, sir, I naught. I is equal to, we say, I naught. And then we say 1 minus e raised power minus t by tau. We say this is tau, because t is equal to tau. This will be e raised power minus 1. So e raised power minus 1, I can write it something like this. I naught 1 minus e raised power minus 1 is 1 by e. And we can write it something like this. I will be equal to, we say, sir, I naught 1 minus 1 by e. Value of 1 by e is 0.37. Okay, so I is equal to I naught into 0.63. I is equal to I naught into 0.63. What does that mean? What does that mean? That means at t is equal to tau, the current has reached the 63% of its we say maximum value, because at time constant tau, current is maximum 0.63% of maximum current, that is 63% of maximum current. So current has reached the 63% of its maximum value. Is this clear till over here, each and every single point I told you? Is this clear over here, each and every single point I told you? Let me know in the live chat if this is clear to each and everyone. If this is clear to each and everyone. Let me know. Everybody give me a signal in the live chat. Graph between I versus t. Current versus time. This is current and this is time. And next one, I ask you to plot the graph between, we say, di divided by dt and time. Di by dt and time. Di by dt and time. And next, I ask you to plot the graph between we say VR and time. And then I ask you to plot the graph between VL and time. Is that clear? Is that clear, guys? Let me know in the live chat if this is clear to every one of you. See. I'll tell you over here. When it comes to current versus time, if you have to make the graph between current and time. Now, in case of growth of current, see, sir, when it comes to the growth of current, initially current is 0. And then after some time, current reaches the maximum value at t is equal to infinity. So we say, and the growth is exponential growth. So we say it is something like this. It is something like this. Initially at time t is equal to 0 and at t is equal to infinity. So current is maximum. Current is maximum. At t is equal to 0, we say current is equal to 0. But when it comes to the di by dt, sir, initially at di by dt, we say current is maximum. We say di by dt initially is maximum. Okay. And then when t is equal to infinity, it becomes 0. So we say at t is equal to infinity, we say di by dt is equal to 0. We say di by dt is equal to 0. You can see over here, di by dt is equal to 0 at t is equal to infinity. So the graph would be something like this only. And if you make the graph between VR and t, sir, it would be something like this only. Because Initially at t is equal to 0, Vr is equal to 0. At t is equal to 0, Vr is equal to 0. And at t is equal to infinity, we say Vr is equal to maximum, because at t is equal to infinity, current becomes maximum, so Vr is maximum. And when it comes to the VL, VL is potential difference across inductor. Potential difference across inductor. So graph would be something like this. Because at t is equal to infinity at steady state, we say, sir, this VL is 0. And at t is equal to 0, VL is maximum. VL is maximum. Is that clear? Is that clear? Is that clear? Is that clear, guys? Is this clear to everyone? This will take furthermore 30 to 40 minutes, okay? We are done in 30 to 40 minutes. Now see, is this clear? Let me know in the live chat, everybody of you. Okay, great. Let's talk about this question. This is the question which is compare the brightness of the bulb at t is equal to 0 and infinity. Can I say, sir, at t is equal to 0, it is initial state. We say, sir, current is equal to 0. Yes. So at t is equal to 0, current is 0. In only in that branch, you just mention it. Only in that branch where inductor is present. Inductor is present. Okay. Like we say, sir, when current leaves from the battery, this is the current. So current will flow over here. Current will not be 0 initially, but in this case, current is 0. Current is 0 at t is equal to 0. Because at t is equal to 0, current is 0. If no current flows through the bulb, it will not glow. So current flows through the bulb, it will glow. So we say in this case, B2 is equal to 0 and B1 is not equal to 0. So brightness of the first bulb, it will glow. B2 is equal to 0. Now, if I talk about at steady state, t is equal to infinity. Listen to me very carefully. Sir, when it comes to infinity, sir, current will be maximum. We say I is equal to maximum. Now, listen to me very carefully. And current will be maximum when it comes to potential difference across resistor, that is maximum. That is maximum. And potential difference across inductor, that is 0. That is 0. Now, if I say current leaves from this point and some current will enter this and some current will exactly enter this. Forget about the current. Let's not discuss it with the help of current. We say this battery gives the potential difference to this branch and this battery gives the potential difference to this branch also. Okay. Now, over here, at t is equal to infinity, we say potential difference across this is 0. VL is 0 at t is equal to infinity. Because we recently studied at t is equal to infinity, sir, VL is equal to 0 because di by dt is 0. Now, if potential difference across this is 0, so this behaves as a simple wire. So, all the potential difference of this branch will be given to bulb only, Now, in this case, potential difference will be shared between this one and this one. This is the resistor. I say, sir, finally, check that branch. Check that branch. In which inductor is present? We say, sir, potential difference in inductor would be 0. Potential difference in inductor would be 0. So, see, let's suppose I say potential difference is 10 volts. So 10 volts will be across this branch also because they are in parallel. Across this branch also. Okay, let me just show you something like this. This will make you understand. If I say, sir, potential difference across this is 10 volts. So we say over here, let's suppose this will take 5 and this will take 5 volts. Okay, they are sharing the potential difference. And sir, potential difference across this branch also will be 10. Why? Because they are parallel. Okay. Now, finally, we say across this potential difference is 0. Why? Because finally at steady state potential difference across inductor is 0. So whole 10 volts will be given to this bulb. If potential difference is more, so it will glow more because power is equal to V square by R. So if potential difference is more, power will be more. So in this case, sir, bulb B2 will glow great more than B1. Is that clear, guys? Is this clear to each and everyone? Is this clear to each and everyone? Okay. Is this clear to each and everyone? Let's solve this particular question over here. Let's solve this particular question over here. See guys, find the current passing through the battery at t is equal to 6 seconds. This is the battery, this is inductor, and this is resistor. We have to find the current in this one and this one. Let's suppose I is the current which leaves from the battery, and I1 is the current in this one, and I2 is the current in this one. Now you tell me one thing. Let's first find we have to find I. Let's first find the current in the resistor. We say V is equal to I2 into R because current in this is I2 into R. So we say over here I2 is equal to V. V is how much? Potential difference is 20 divided by R. R is how much? That is 10. So that is 2 ampere. Current in this is 2 ampere. Let's find the current. This was actually asked in the IIT. Let's find the current in this one. Now see, we say, sir, V is equal to L di divided by dt. This is the potential difference in case of inductor. In case of resistor, this is the potential difference. Take this dt over there. We say V dt is equal to L di. Now integrate. Sir, take this V out because it is constant. This is V dt integration. This is L integration of di. This and this will cancel. So V into T will be L into I. And over here we say, sir, I will be simply V divided by L into T. So I can say, my dear friends, this I is simply, I is equal to V. What is the value of V, my dear people? Value of V is 20 volts over here. That is 20. Divided by, what is the value of L? L is given as 300 over here. Multiplied by, what is the value of time? Time is given as 6 seconds. 3 into 2 is 6. I1, this is I1 is equal to 40 ampere. Now we have to find I1 plus I2 net current. So that is I is equal to 40 plus 2, which is equal to 42 ampere. Is this clear to each and everyone, guys? Is this clear to each and everyone? Let me know in the live chat. Let me know in the live chat. Let me first finish this topic and then we'll do the question. Decay of current. What does decay of current mean? See, you guys knew the growth of current. Now, what does decay of current mean? Decay of current means decrease in current. Now, see, as current has reached the maximum value, We studied current reached the maximum value. Now listen to me very carefully. When decay of current started, listen to me. We say, sir, at t is equal to 0. Let's suppose this is the circuit over here. First, if you connect this key with this circuit, means upper circuit is connected. Leave this lower one. We say over here, my dear people, that, sir, when you close the switch, when you connect the switch, this battery will basically send the current, and that current will reach the maximum value after some time. Now, after reaching the maximum value, what you do is that you connect this 1 and 2. You connect this 1 and 2. Now, this middle part is open. No current will go over here. No current will flow in this part. Now, this is the circuit. This is the circuit. I'll make the circuit over here. I'll make the circuit over here. Let me just make the circuit over here. This is R and this is, in this case, L. Now we say, sir, this inductor is charged. This inductor has got current in it. Now at t is equal to 0, we say current is maximum, I maximum. Okay. Now this will start giving the current to this resistor. Okay. Because current will now do what? Current will start decreasing. Current will start decreasing. See, initially you were charging the inductor. In case of growth of current, you were charging the inductor. And this is also called discharging of inductor. So while you connect this and this, now this is the circuit. So now this will send the current. This will give the current. In the growth of current, it was taking the current. See, over here, current was flowing in the inductor. So it was getting charged. Because whenever current flows in the inductor, it gets charged. E is equal to 1 by 2 Li square. And over here, my dear people, over here, we say, sir, it is giving the current because it has already got the maximum current. Now it will say, now you take some current, some current. Now we say current is maximum. Now this is what we call initial state. Initial state. And we say, sir, finally, at t is equal to infinity, we say current will become 0. Why? Because current is decreasing right now. Now the question is, if I say, sir, no inductor is present in the circuit, will the current reach the 0 value instantly? Yes. But because of the inductor, it opposes the change. It will not let that happen, that current will become 0 instantly. But current will become 0, but after some time. It will be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so we say here current is decaying and becomes 0, but not immediately. Because of inductor. Okay, inductor opposes the growing current and inductor supports the decaying current, decreasing current. This is the case over here. Now, my dear people, listen to me very carefully. If I say, sir, at t is equal to 0, current is maximum. At t is equal to infinity, current is 0. If I say in between, if I say in between, we say at t is equal to t. What is the value of current when current was decaying? So the value of current at t is equal to t is I naught, then we say e raised power minus RT divided by L. This is the value of current when current was actually decaying. Right now, I gave you the perfect example. Initially, while you connect this key with this one, so it gets charged. So after completely charging, after reaching the maximum, current reaching the maximum value, then you connect this with this one. So now this becomes the circuit. Now this starts getting discharged. It will give the current now. Current will decay, decrease. Because of inductor, it will take time in decreasing. And that's what we call the decay of current. Decay of current. Okay. So at time t is equal to t, we say how much is the current. This is the value of current. Now we know as time constant. When it comes to the time constant, we say, sir, tau. It is L divided by R. Now, if you do it 1 divided by tau, that will be R by L. If you put in the above equation, we can write I is equal to I naught. I naught is the peak current. E raised power minus, instead of R by L, we say 1 by tau. So we say T divided by tau. We say I is equal to I naught. We say E raised power minus T by tau. Okay. This is the value of this one. Now, my dear people, if I just say, if T is equal to tau, if the time value of time is tau itself, then what is the current at that time? How to find the current? Put the value of time. I is equal to, we say, sir, I naught. We say e raised power, this will be minus 1. And further we can write this as I is equal to I naught e raised power minus 1. So e raised power minus 1, that is 1 by e. We can write 1 by e. So we know value of 1 by e is 0.37. So we say I is equal to 0.37 into I naught. So time constant is that time. Time constant is that time. Listen to me very carefully. I'll write the definition over here. We say this time constant is that time after which the current becomes 37% of its maximum value. Okay? Time constant is that time after which current becomes 37% of its maximum value. I hope decay of current is clear. I hope growth of current is clear. Is that clear, my dear people? Is that clear? Now comes this particular topic over here. Let me know in the live chat if this is clear to each and everyone. If this is clear to each and everyone. Okay, now see, mutual inductance. What does mutual inductance say? See, let's suppose we have a coil over here. The radius of the coil is R1. And the current is I1, which is flowing in the coil 1. And then we have a coil 2 over here. The radius of the coil is R2. Okay. Now we say over here, when it comes to the coil 1, we say due to the coil 1, magnetic field is produced at x distance. Sir, we have studied when you have a coil in which current is flowing, because of this at x distance magnetic field is being produced. And we say that magnetic field is crossing the coil 2, which crosses the coil 2, over here. And if that magnetic field crosses the coil 2, listen to me very carefully. We say, so flux is produced through coil coil 2. So flux is produced through coil 2. So flux is produced through coil 2. Okay. Yes, sir. If flux is produced through coil 2, my dear people, listen to me very carefully. If flux is produced through coil 2, we say, sir, this flux through coil 2 is directly proportional to the current in coil 1. Sir, if more current flows through coil 1, because of this, more magnetic field is being produced at this point. Sir, because of that, more flux will be produced through coil 2. Yes. Now replace this proportionality with a constant. We say, sir, that phi 2 is equal to M into I1, where M is the mutual inductance. Mutual inductance. Okay, where M is the mutual inductance and is constant. Okay. Now the question is, what is the value of M? Like in case of self-inductance, we used to have one coil only. Like in self-inductance, we have this coil. Listen to me very carefully. In one coil only current is flowing, magnetic field is being produced, and we say over here EMF is induced in the same coil. Everything was happening in the same coil only. That's why we call it self-induction. But when it comes to the mutual induction, over here, this will create the magnetic field. Because of the magnetic field of coil 1, we say EMF is being induced or flux changes in the coil 2. Now, I'll give you the feel of this one. Don't worry. So here we have two coils. That's why we have mutual induction. Now see, we say, sir, this one. Now, when it comes to basically this M, the value of M is simply, we say mu naught, say R1 square, R2 square. Okay. Then you have pi divided by, we say x cube, and put the 2 over here, that is 2x cube. So this is the value of M. This is the value of M, that is mutual inductance. This is the value of M. What is R1? R1 is the radius of first coil. R2 is the radius of second coil. X is the distance between the two coils. I'll make you understand once again. If we have a coil in which current is flowing, because of that current, magnetic field is produced over here. That magnetic field is crossing this coil. So flux is being produced in this coil. So we say flux is proportional to the current. So replace this with a constant, that is M. So this M is called mutual inductance, and the value of M is mu naught R1 square R2 square pi divided by 2x cube. Now if I say, my dear people, if current in coil 1 is changing. Now, if current in coil 1 is changing, so magnetic field due to it is also changing. We say magnetic field due to it also changing. Okay. So flux through coil 2 is also changing. So we say, sir, if you are sending increasing, if the current in the coil 1 is increasing, because of this increasing current, magnetic field at coil 2 is increasing. Because of that magnetic field, flux through the coil is also increasing. So flux is changing. So can I just write from the equation 1 as, so we can write, listen to me very carefully. Sir, we can write, sir, if current is changing, can I write this current is simply di divided by dt? Yes, sir. And then you have mutual inductance M, and is equal to, from this side, you were having phi. So you say, sir, that is d phi divided by dt. Because by changing the current, flux also changes. By changing the current, flux also changes. Now, you guys tell me one thing. You guys tell me one thing. As from Faraday's law, can we say, sir, this EMF is equal to d phi by dt? If flux through the coil changes, we say, sir, EMF is being produced. So flux over here is changing. So we say this is EMF. Instead of d phi by dt, we say EMF is equal to m di divided by dt. M di divided by dt. So production of this EMF, this is what we call the mutual induction. When we say when EMF is induced in a coil, by changing the magnetic field of another coil, the process is called, we say, mutual induction. Again, I'll explain you this particular concept. Let's suppose we have this coil over here. In this coil, we say you are sending this current which is changing, okay? Sir, because of this changing current, EMF is being induced in the coil. That EMF is minus L di by dt, or if we take the magnitude only, we say L di divided by dt. This EMF is being induced in the same coil only. Because this current is flowing in the same coil, EMF is being induced in this coil only. So this is what we call the self-induction. But when it comes to the mutual induction, you have one coil, you have another coil, okay? And in this case, sir, current is flowing in this coil. We say EMF is being produced in this coil. And this EMF is what we call M di divided by dt. Okay, by changing the current in this coil, EMF is being produced in this coil. This is what we call the mutual induction, and this is what we call the self-induction. I hope there remains no doubt afterwards. Is this crystalline clear? With the fire emojis, this was the last topic, and I have 2 questions left. I'll solve those and we are done. Is this crystalline clear? Let me know with the fire emojis, guys. Everybody, I want all of you to comment down right now. With that Josh. Everybody. And make sure you like this particular session if you have not liked it. Okay, let's solve this particular question over here. So the ratio of initial to final current when the battery and the switches go. See, you have got the circuit over here. We say at time t is equal to 0, we know, sir, current is equal to 0. But in that branch, where we say, where inductor is present. So in this case, we say current is 0 at t is equal to 0. So at t is equal to 0, this circuit would look like, see, what we are supposed to find, ratio of current. So at t is equal to 0, we say in this branch, current is 0 because inductor is present. So we remove this, so the circuit would be something like this. This is R, this is switch, battery, and this radius R. This is R. And this is, let's suppose, E. So in this case, current I is equal to, let's call it I initial. This I initial is equal to V by R. V is E. And R is how much? R plus R is 2R. This is current initially. And let's talk about finally. Sir, finally at t is equal to infinity, we say current is maximum. And if current is maximum at t is equal to infinity, we say in that case current will flow here also, and this behaves like a simple wire. Because at t is equal to infinity, I told you VL is equal to 0. Means this is a simple wire. So at t is equal to infinity, the circuit would be something like this. This is R, this is R, and this is R, this is E. Now find the value of current at t is equal to infinity. So we say over here, see R, R and R. This R and this R are in series, in parallel. So this will be R equivalent in this case will be R by 2. These two have equivalent R by 2. And that is in series with this one. That is R by 2 plus R. That will be how much? 2R plus R is 3R by 2. This is equal to the R equivalent. Now current will be I is equal to V by R. V is E. Divided by R equivalent over here is, we say 3R by 2. 3R by 2, and that I'll take over here. This is I final. Now if I have to write I initial divided by, we say I final, it will be simply I initial upon I final. I initial is E by 2R. We say it is E divided by 2R upon I final is how much? 2E by 3R. We say 2E divided by 3R. So it will be simply E by 2R multiplied by 3R by 2E. This and this will cancel, this and this will cancel. That is 3 by 4. Ratio of current is 3 by 4 initial to final. This is your homework. Okay. And now we have boys and girls. We are done with the entire chapter. Thank you so much. Thank you. Okay, guys, let me just tell you one thing. Make sure you like this session. And the second thing is, I am ending the live stream right now. Make sure you comment afterwards, okay? I want all of you to tell me in the live, not in the live chat, once I end the stream, in the comment box, how was the session, each and everything. Because whenever we read your comments and you write those nice things, the genuine things only, okay? Don't write like you are buttering the teacher, no. Write the genuine things, okay? Whatever it is. And when we read those comments, it gives us energy. It gives us that high josh. So that's the reason we come over here and teach you for these longer sessions, okay? So thank you so much. This was all about it. Take care and bye-bye. See you guys in the next session, and comment down below right now only. Okay. Thank you so much, guys.